Yes. All right. So hi again, everybody. Thanks for joining. This is the final review session for fall 2022. And I spend a lot of time like preparing for these review sessions. So hopefully the review session today is gonna like be very intense, but like should be very relevant for your studying and hopefully helps you in like organizing your ideas in problem solving. So the main thing I want to do today is this general problem solving strategy, which is just I want you to be able to look at a problem and realize the approach. What am I doing in this problem? And then we're going to apply this to all the different situations here. So the situations we have are rotations and translations, collisions involving rigid bodies, circular orbits and elliptical orbits, simple harmonic motion, and then we'll also talk a little bit about Coriolis. So are we ready? Any questions before we start? Can you hear me well? Everything okay? All right. So the summary of like the problem solving in 821 is right here. And I have talked about this before in several classes that I taught, but this really is what I want you to know about how to approach a problem. So you can really summarize the problem solving of this course into two pieces, two categories. Dynamics, which is basically Newton's second law. That's one way to approach problems. The other way is using conservation laws. And in conservation, we have three different approaches, like conservation of energy, momentum, and angular momentum. So in any problem that you see, I want you to start by asking yourself the question of, is this a dynamics problem or is this a conservation law problem? So let's talk a little bit about how do we know whether we're doing dynamics or not. So dynamics means, as I have it here, F equals ma for translations, and torque equals I alpha for rotation. These together are Newton's second law, which is dynamics. So dynamics is usually a difficult approach. Like usually looking at a problem from Newton's second law is more difficult than using conservation. So we try to avoid using dynamics as much as we can. So we really use dynamics only when we really have to use dynamics. So when is that the case? These quantities that I wrote right here on the left-hand side, these are the dynamics quantity. So acceleration, if the question wants the acceleration, either angular or linear, like alpha or a, then you have to use dynamics. You have to use F equals ma. You cannot find acceleration otherwise. So you really should look at what the question is asking about. Is it asking about the acceleration, A or alpha? Then you need to use dynamics. It's a dynamics problem. Is it asking about some force, like what is the normal force? What is tension? What is friction force, static friction? Then that's a dynamics problem again. Because forces and acceleration, that's F equals ma. Also time, any question involving time is a dynamics question. Like how much time does it take to fall down? How much time does it take to do this? That's a dynamics problem because time is only involved in acceleration when you find the acceleration first and then you integrate it to find, like you do kinematics with it. By integrating the acceleration, that's where time shows up. So time is the kind of the integration of the acceleration. Anything involving time, force, acceleration is dynamics. Other than that, if the question doesn't want any of these dynamical quantities, you go to the other side and you say, okay, this is a conservation law problem. What is conserved? That's the other thing. So you go there and say, okay, is energy conserved? Is momentum, is angular momentum conserved? And we're gonna practice on this. And I have this remark in blue, which is, okay, dynamics is all about finding the acceleration or some force or time. Part of like acceleration, interest in acceleration comes into circular motion and simple harmonic motion. Because circular motion is all about the centripetal acceleration. Like we know something very special about circular motion, which is the v squared over r centripetal acceleration that exists in circular motion. So that's why any circular motion problem is dynamics, because you want to show, like you want the acceleration, the centripetal acceleration to show up. So circular motion is dynamics. Simple harmonic motion is also dynamics, because in simple harmonic motion, the oscillation, your target is to show that the acceleration looks like this, just like minus a constant times a position. So again, it deals with the acceleration. Simple harmonic motion deals with acceleration, so it's dynamics. Circular motion is dynamics. So even if the question doesn't ask for the acceleration immediately, simple harmonic motion is dynamics, circular motion is dynamics. Other than that, you think about conservation laws, and we'll talk about it. Any questions? All right, so we're going to apply this to different problems, but like a very important remark that I have down here is, again, I'm going to send you these notes and everything after the session. So a very important remark is, now that we're dealing with rigid bodies that can rotate about their own center of mass, we have to draw the free body diagram. So whether you're doing dynamics or you're doing something that's conserved, you have to draw a free body diagram. Either way. The free body diagram is no longer looking like the left, where it's just like a block, a point mass, and the forces all are like at the same point. This is wrong. We don't do that anymore. Our free body diagram should be like this, where every force is kept exactly at the location where it's acting. Because it matters. It matters for torques and for angular momentum. It matters where the forces are acting. So you should keep your rigid body as it is, like a sphere is a sphere, a wheel is a wheel, etc. And then put the forces from the location where they are acting, not from a random point. So what I'm saying is, like, mg is from center of mass. Put it at the center of mass, always, mg. Normal force and friction come from the ground. So they both act from the ground. Very important. Keep every force exactly where it is acting. It's acting from one point. So our free body diagram should respect that. Okay? Because torques depend on the locations of forces. Any questions? Yes, we will talk about this. So let's apply this immediately to different situations and see. So I'm going back to PSET number 9. So I'm using a combination of PSET problems and practice problems that I see to be a good combination of like relevant ideas here. So I'm going back to PSET number 9. This is like the pulley problem. We have discussed pulleys at the very beginning of the course, review session number 1, exam number 1. And now we're back to them with the idea that the pulley is no longer massless. It's a rigid body. It's an actual thing that can rotate. So now we can deal with it realistically with this rotation of the pulley. And if you remember from the first review session, which focused a lot on pulleys, and then it just happened this year, we didn't really ask a full question about pulleys in the first exam, but it is like an important idea, very important idea. So we're back to it here. And if you remember, there was something, some kind of approach I told you about pulleys. I want to use it again here. So in terms of the big picture right here, this is a question is asking, find the acceleration of object 1 or 2. So finding the acceleration, that immediately means we should be using dynamics. Done. So that's the first question you ask yourself. Dynamics or conservation? No, dynamics. Why? Because I need the acceleration. So we're good. The second thing, once you determine you want to do dynamics, you want to draw a free body diagram of every moving object. Some of the objects, like now we're dealing with rotations and translation. Some of the objects will be translating. Translating means linear motion. They are moving linearly. And some of the object will be spinning. That's the rotational motion. And then some of the objects, generally speaking, some of the objects will also be doing both at the same time, translating and rotating. Pulley problems like this one, they are separate. Like this object number 1 is translating. It's not spinning, it's just purely translating, while the pulley is purely rotating, etc. The emphasis of the final exam is on the material after the second lecture, which is exactly the emphasis I'm doing in the review session. I put a lot of thinking about it. So what we're covering in the review session and like the practice problems on MITx as well, that's the focus for the final. Okay, so object 1 is translating, object 2 is translating, pulleys are rotating. So here we have this split between rotations and translations, but we don't care. We use dynamics. Dynamics means if you're translating, you write F equals MA. If you're rotating, you write torque equals I alpha. So let's go through these and like remember our strategy for pulley problems. So the first thing I told you about, you have to draw free body diagrams, but also you need to choose coordinate systems for each of the objects. So if you remember from like the pulley problems from before, I advise you always to try to make your accelerations positive, so you don't miss any minus signs, and also the algebra simplifies. So this still works here. So let's see what I'm talking about. I know that object 1 is going down. The question is telling me M1 is bigger than M2, so M1 is like going down. So for object number 1, I'm going to choose the acceleration, sorry, the J hat to be down. Why? Because it's like the acceleration is down. So I just match for pulley problems, like my advice is to match the acceleration to the coordinate system. Object one is going down, then I'm gonna choose j hat down there. But object one is gonna move up, I'm gonna choose j hat up, and this is fine. It's fine that every object has its own coordinate system, that's okay. Okay, so as object two is accelerating up, the j hat is up there. That's my choice. And then when I go to the pulleys don't translate, they spin, they rotate. So again, I'm gonna look at the sense of rotation that they are doing, the angular acceleration for them, and I'm gonna make this a positive direction for rotations. So as object one goes down, the pulley basically rotates in this way. That's alpha of the pulley. To match, like the whole system here goes together with the same acceleration, by the way. Like we don't really have to worry about constraint conditions between the different accelerations because everything is connected together. So the magnitude of acceleration is all the same. So there's A1 and A2, but they are really the same thing. And alpha for the pulley A is going like counterclockwise. And alpha for pulley B is also going counterclockwise. So I'm going to choose a coordinate system that obeys that, makes these accelerations positive. So if you want to make a counterclockwise rotation positive, then out of the page is your k hat. That's how you say the coordinate system for rotations. Coordinate system for rotation is all about k hats because all the rotational quantities are vectors in k hat. Like torque is in k hat or minus k hat, alpha, omega, all of these are in k hat. So for rotational motion, you need to define k hat to tell me what is the direction for positive rotations. So here, as I know, the pulleys are rotating in a counterclockwise sense, I'm gonna match this direction and say this is positive. So k hat is positive. That's my choice here for both of them. Why now both these alphas are positive and both of these A's are positive as well? They don't need to be the same, but it just happens that both of them are rotating, spinning in the same exact manner. So it makes sense to just use the same k hat for both, but it doesn't have to be the same. So my advice is just choose coordinate systems to make the accelerations positive, both A's and alpha. So what happens now is the following. Let's look at the free body diagrams from each of them. We're doing dynamics, so we're doing F equals MA and torque equals I alpha. So for the translating object, like object number one, it's MG, it's tension, we're gonna call it T1. And I told J hat to be down. So the equation here, remember from the pulley stuff from before, I told you to focus on each of the blocks, each of the objects, and find one equation of motion for that object. And if you remember, I told you to add these equations to get the algebra very easily. So that will still work. Let's just see how it works. So for object one, this is the equation. It's M1G that wins, is positive, minus T1 is M1A. That's your first equation. And I'm just saying A1 is A2 is A. I'm not like looking at different, they are all having the same magnitude of acceleration because they are connected directly and all the pulleys are fixed. Any question about equation one? Okay, I'm gonna go to object number two, very similar, except let's go in order. So let's go to the pulley A. So if you look at the pulley number A, this is how it looks. Again, it matters where the forces are acting. So there are two tensions acting on the pulley. There's tension one acting from this side right here down. And there's tension two acting from there. And don't forget, yes, you only need a constraint equation if one of the pulleys can translate. If the pulleys are fixed in place, then yeah, you don't have to worry about it. So the tension, the two tensions on the pulley, don't forget this, they have to be different because the fact that this pulley is rotating means the torque, there is net torque acting on it. If these two tensions were exactly the same T and T, then there will be no net torque on it and it will not rotate. So the fact that the pulley is spinning means that T1 and T2, the tensions on the sides are not the same anymore. And we said K hat is out. So now the equation here, both of these have the same radius R. So the torque they create is just the force times the perpendicular distance to the center of mass. So don't forget this, torque is force times the perpendicular distance. T2 is the one that is negative. If you look at the torque, so now look at T2 and T1. T2 is trying to make the pulley rotate clockwise. It's pushing to the right, so it's trying to make it rotate clockwise. That's negative torque. While T1 is pushing from below here, from the side, so it's trying to make it rotate counterclockwise. So it's T1 here that is creating the good torque, the positive torque that makes it rotate in the K hat. So what I'm saying here is the torque T1R is positive and the torque T2R is negative. And this just sums to I alpha, and I was given here to be mass of the pulley times R squared alpha. Okay. So that's my second equation. Torque sum to I alpha. Why torques? Because this is rotating. Any questions about the signs of torques or anything here? Okay, and similarly, you can go to this next one. So now it is it's T2 this way and T3 that way. So now if you look at the same thing, it's now T2R is positive and negative T3R, because that's the other way, the clockwise, and it's 1/2 MBRB squared alpha B. Sum of the torques is I alpha. Any questions? No, you don't need to know any moment of inertia. You'll be given the moment of inertia. No, you'll be given that. You will be given the moment of inertia about the center of mass. And then in some contexts, you will need to choose to do the parallel axis theorem. So that's something you need to think about. If the object is not rotating about center of mass, you need to add the parallel axis theorem to it. But ICM will be given. A1 is equal to A2 equals to A because all the pulleys are fixed. We don't have moving, like translating pulleys. And I don't think we're gonna worry about that in the, like, I think all of the pulleys at this point might be just fixed like this, so all the acceleration are the same. So, and then finally for object number 2, J hat is up, so T3 minus M2G is equal to M2A. So these are my 4 equations from the 4 objects. F equals MA for the translating, torque equals I alpha for the rotating. Okay, Stella, are you asking about in the torque or in the force equation? If you're asking about the torques, it's all about the direction of rotation that this torque is trying to create. So look at pulley B. This is B. This is A. So for pulley B, T2 is pushing this way. So it's trying to make it rotate counterclockwise, which is what we defined as positive. But T3 is pulling down from here. So it's trying to make it spin clockwise. I don't know if you can see that easily or not, but that's the way I think about directions of torque. What is the sense of rotation they're trying to create about center of mass? We defined counterclockwise to be positive here. By saying K hat is out, we're saying counterclockwise is positive because counterclockwise corresponds to out of the page. So choosing K hat out means we're choosing counterclockwise rotations to be positive. So that's why I'm deciding in the torques. A torque that creates a counterclockwise rotation is positive. A torque that creates a clockwise rotation is negative. Any further questions here? Okay, 1 second, someone is not. All right, so now, like, these are the 4 equations, the rest is algebra, but like we're still missing something, which is that alpha of the pulleys is related to the acceleration A. The whole thing has to accelerate together. So we have this constraint relation that you don't have to prove, like we know it from circular motion, that the alphas are just, like the A is alpha R, basically. This is equation coming from circular motion, the tangential acceleration of the string versus the angular acceleration of the pulley have to match by the radius. So these alphas are just A over R. Okay. So that's always the case in a pulley problem. So what do we do now? Like, let me just show you this very quickly. So I'm gonna replace the alphas in the equations here. I'm gonna replace them by A over R. So this guy right here is A over R, and this is A over R. So when you do this, the R's should cancel out in the equations like A and B for the Pauli equations. Let's look at what happens to the radius R. There is R canceling one of these R's, right? Same thing down here. And then the whole equation has an R, like TR minus TR is 1/2 MAR. So this other R, you can just divide by it and cancel it as well. This R goes with this R, goes with that R. R. And now you can add the equations like the trick I told you about very early in the semester. This is the easiest way to do the algebra. You have 4 equations and 4 unknowns. If you try to substitute and do stuff, it's okay, but it's gonna take you some time. But if you stick to this idea of make every acceleration positive, you don't have to worry about any minus sign between A and alpha. They're all positive, so everything is positive. And if you add the equations, it should always work out. But just make sure that you divide by the radius first in the torque equations to make it look like a force equation. That's the algebra step. Divide by the radius in the torque equations. Now let's see what happens if you just add the 4 equations here. If everything is correct, then all the tensions, all the intermediate tensions will cancel out and you get the acceleration immediately. Let's see what happens. There's a minus T1 here. There's a plus T1 there. So they will cancel on this side. There's a minus T2, the plus T2, minus T3, plus T3. If this didn't happen, then you made a mistake. So that's another way to check your work. The tension should always appear in opposite signs in the equations. Minus T1, T1, minus T2, T2, minus T3, T3. So that's why when I add everything together, I just get very simply M1G minus M2G, everything other than that canceled on this side. And then on that side, I just have the acceleration times some factors. So I have what? I have M1 plus M2 plus 1/2 MA plus 1/2 MB times A. Done. Divide by that factor and you got the acceleration. So we found the acceleration. So that's like the easiest way to do the algebra and Pauli problems. And we talked about that in the first review session. Some of you were upset that there were no Pauli problem there, but it's still like an important. Did anyone have trouble like getting into Zoom? Because someone is telling me they cannot access this. Okay, so that's one category of problems, which is a pure dynamics problem. F equals ma, torque equals I alpha, and that's kind of coming back to Pauli problems. And just make sure your accelerations are positive, then the algebra should simplify like this. Any questions about this approach for Pauli problems? Okay. Okay. She got in. Okay. Any questions about this application? So that's one type of problem. So my target today is to cover as many relevant types of problems as possible and just show you that the strategy is the same. We're thinking dynamics or conservation. And then if you're doing dynamics, this is kind of what we do, free body diagrams and writing down forces or torques or torques. We could write both. Any question about the Pauli problem and the addition of the algebra? All right, so let's move on to the next type of problems where this Pauli kind of problem doesn't mix rotations and translations. In this kind of problems, the blocks are translating linearly, the pulleys are rotating. So each one is just doing one kind of motion. So the next level of difficulty is when you have something that is both rotating and translating at the same time. So that's rotations plus translations. So let's just write this down here, rotations plus translation. So we have an object now that is doing both at the same time. So this is just like a wheel, right, that is moving and spinning at the same time. So the very important idea I want you to understand here is that these two are two separate degrees of freedom. These are two separate ideas. The motion of the center of mass, like this VCM and ACM, this covers the translational motion of the object. So the way we talk about how this object is translating, moving linearly, is just through how the center of mass is moving and accelerating. So there is VCM and ACM, that's the translational motion. The object at the same time can be spinning. So this spinning is characterized by the omega and the alpha. Like this is the velocity and the acceleration, right? So the important thing to realize is the following. Generally speaking, there is nothing relating omega to VCM and alpha to ACM. These are two separate ideas. Like, let me write it here. Generally, the object can go in any kind of motion. ACM doesn't have to be alpha R, for example. VCM doesn't have to be omega R. You can translate in any way and rotate in any different way. The typical example we give you here, we give you in a PSET, I think, is you can throw a bowling ball forward. So you're throwing it forward, it's translating forward, but you can give it a backward spin. As you throw it, you can make it spin backwards. So the ball is spinning backwards and moving, translating forward. The spinning, the rotation, and the translation don't have to match at all. So the general situation is you can be spinning in any way and translating in any different way. That's a very important idea right here. Any questions about that? And there are names here, like there are names for these different kinds of motion, like slipping and skidding. I don't think the names are important, but the important idea is, generally speaking, VCM and ACM, the translational motion, doesn't correspond at all to the rotational motion of the same object. It can do whatever it wants separately in these 2 degrees of freedom. You can spin backward and move, translate forward, okay? Unless we're talking about a very special case, which is rolling without slipping. So rolling without slipping, that's the only important name. So the name, the word rolling without slipping means, okay, we're not talking about this general kind of motion. We're talking about some specific special case. The special case is rolling without slipping. So you have to be very careful in these problems about rotation and translation. Are we doing rolling without slipping or no? Because generally speaking, you cannot say VCM is omega R and ACM is alpha R. This is not true, except for rolling without slipping. So in rolling without slipping, yes, VCM is omega R and ACM is alpha R. Just means that the translational motion kind of matches the rotational motion. That's a very particular kind of motion when you have like a sphere. I have something here that's almost probably not. So I'm doing this in my office. First time I do a review session from my office. I usually do it from home. So kind of feels a little weird. But anyway. So yeah, so the rolling without slipping is just the fact when you just roll a ball or something, so it rotates and translates together. Like kind of the translational motion comes from the rolling, from the spinning. They come together, they move together, and there is a geometrical proof of this fact. But this really is the important idea. Generally speaking, translation and rotations are not related of the same object. If it's rolling or slipping, that's a perfect special case of VCM and omega matching exactly. So VCM is omega R, R being the radius between center of mass and the contact point. That's R. That's what I mean by R, generally speaking, between center of mass and the contact point that you're rolling about. Okay, any questions about that? So I have this table right here. There are 2 different kinds of motion. The general motion, which is called slipping or skidding, or I don't care about the name. That's the general kind of motion. VCM has nothing to do with omega R and ACM has nothing to do with alpha R. If we're rolling without slipping, that's a very special case. VCM is omega R and ACM is alpha R. Any questions? Okay, so that's one thing about the difference between these 2 motions. The second thing, there is a second result from that, which is friction. As the object is going in this motion, either rolling or like slipping or skidding, doing whatever, there's friction. There could be friction from the ground. So very important idea right here is the following. Let's look at the case, the general case. This again is the general case, not rolling or slipping, any kind of motion, okay? So what happens as this object, let's say, is moving, translating with VCM like this, and let's say it's like having an omega like that. And as we said, these 2 are not related, generally speaking. The ground, which comes like friction, comes from ground. The ground does not interact with the full object. It only interacts with the contact point down here. It sees the object just from the point on the ground. The ground doesn't see center of mass, doesn't see any general point. The ground only comes here at the contact point. So that's why let's look at this contact point, which is what the ground sees. This contact point has two different types of motion. It is translating because the whole object is translating forward. So here, this contact point is translating forward with VCM because the whole object is going with VCM. But at the same time, the spinning of the object gives it a circular motion kind of tangential velocity, like the omega of the object. If in this sense right here, there will be a different kind of velocity the other way, which is omega r. This is from circular motion. So the contact point relative to ground is moving forward because of translation and also slipping backwards because of the spin with omega r, that's circular motion equation. Any questions about this? Contact point has two instantaneous velocities. So as we said before, VCM is not necessarily equal to omega r in the general case. So these two velocities will not cancel out. So that's why one of them is bigger than the other. VCM is bigger than omega r bigger than VCM. In both cases, this contact point ends up with a net velocity relative to ground. So that's why friction applies, kinetic friction. Very important to remember this. The general kind of motion has kinetic friction, and kinetic friction is kind of easy to figure out. The direction of it is kind of easy because kinetic friction is just always pointing against the motion. So this against the motion of what? Not of the center of mass, the motion of the contact point. That's what matters. So if the question is asking you what is the direction of kinetic, like static friction is a different story. We're coming to that. It's more tricky. So the general case is kinetic friction because VCM and omega r at the ground at the contact point don't match, so they don't cancel out. One of them is bigger than the other. So whichever one is bigger, friction is against it. Friction is against this total motion of the contact point. That's kinetic friction in the general case. Any questions about this? Let's apply it to the concept question in the practice quickly. So we have this case. This is an object translating and rotating at the same time. It's not rolling without slipping. Be very careful. Is the question saying rolling without slipping or no? Here the question is saying specifically that VCM is less than R omega. So this is not rolling without slipping. Okay, so that means what? Means immediately there will be kinetic friction, not static, kinetic friction. Why? Because the contact point is not going to be at rest. And now the question is asking, okay, so the question can ask you, is this friction static or kinetic? You would say kinetic, because it's not rolling without slipping, so the contact point is moving. So there will be kinetic friction against it. How do we know the direction of kinetic friction? Easy, it's just against the motion of the contact point, not the center of mass, not any other point, the contact. The ground only sees the contact point at the bottom. So let's look at this contact point. This contact point is moving with VCM because the whole thing is translating with VCM. That's one kind of motion the contact point is doing. The other one is coming from the spinning. Spinning counterclockwise like this means at the ground here, the tangential speed from spinning is to the right, omega r the other way. We have these two competing velocities at the bottom. Any questions about that? And the question tells us that VCM here is less than omega r, like this is bigger. So the net velocity, like this contact point is kind of moving to the right. Why? Because the omega r is bigger than the VCM. So the contact point is moving to the right relative to ground. So that's why friction just opposes that and goes to the left. So the answer, I think, 7. If I make any mistake, by the way, while doing anything, please let me know. So that's how you find the direction of kinetic friction from the general kind of motion, not rolling without slipping. You look at the contact point, there's VCM and omega r, depending on the context, the directions will change. VCM is just like the VCM, and the omega r coming from the spinning, like match the spinning at the bottom. How does this point go from the spinning? And then see which one is bigger, then friction is against it. Any question about that, finding the direction of kinetic friction? Oh, thanks for letting me know. Yeah, this question was asking about the velocity. The velocity is 3. Thanks. Sorry about that. So velocity is 3. Kinetic friction is 7. Thanks. Hope I didn't confuse any of you. Does this any question? Does this make sense? Yes. Okay, so just explaining again one more time. The contact point has the whole thing is translating and rotating at the same time. So every point on the sphere on the wheel is having two kinds of motion. And I'm interested in just the contact point. This is what matters to me. The contact point right here, the whole object is translating to the left. So the contact point is translating to the left with VCM, same VCM. The whole object is moving translationally VCM. At the same time, spinning like this. The spin here gives it, like, if you look at the direction of this rotation right here, I wish I can. Let me try something. Okay, so it's spinning this way. So like at this point right here, the tangent to that circle is going to the right. So that's the omega r. Like from this kind of circular motion, this point is like going with an omega r to the left. And then it's also translating to the, so omega r to the right and translating to the left with VCM. This contact point right here has these two competing velocities, one from translation, one from rotation. And in this question, it tells you this is bigger. So that's the velocity, the net velocity. So kinetic friction would be the other way if you wanted to find it. The difference between slipping and skidding is like which one of these is bigger than the other. But I don't think that's important. The naming here are important. But like basically, if omega r is bigger than VCM, we call that slipping. And if it's VCM that's bigger, we call that skidding. But I don't think these names are like the only important kind of name is rolling and slip, because when rolling or slipping, these match exactly. So I don't know if this helped, but any questions? So the contact point has two different velocities. One of them is bigger than the other here. So that's the net velocity at the bottom. And kinetic friction will just be against that. Any questions? Yes, yes. Friction, kinetic friction, always in any context, kinetic friction is against motion. You move one way, kinetic friction is the other. So the contact point here is moving to the right, kinetic friction is to the left. So coming back here, so that's the general case. But if you look at the rolling without slipping case, it's a similar picture. So this contact point right here has VCM one way and has omega r the other way. But now they're equal. This contact point is at rest. That's very special about rolling without slipping. No, look, I'm going to come back to that. Like static friction is a tricky, I'm dedicating part of the review. I'm coming to. So compare the general kind of motion, you have kinetic friction against the motion of the contact. Rolling without slipping means immediately you have static friction. Don't forget this. Students often forget about this. They don't include static friction when they do rolling without slipping, because the question will not necessarily tell you there is static friction. You should do it yourself. Once you see rolling without slipping, if you're doing a free body diagram, put static friction. Which direction, that's tricky, we're going to come to that. So the direction of it, let's just put a question mark. But just for now, remember this. Rolling without slipping, there is static friction because the contact point is not moving instantaneously. General motion like slipping or skidding or whatever the name is, general kind of motion, the contact point is moving, so there is kinetic friction against that. Okay, static friction is tricky because the contact point is not moving. So how do you know like static friction, which way it's gonna go? It's not, this point is not moving, like the net velocity is 0. So we're gonna come back and ask and talk about the direction for static friction in a second. But just for now, put this in your mind. You see rolling without slipping, you immediately think there is static friction. Not rolling without slipping, then there is kinetic friction, where just against motion. That's kinetic friction. So we'll come back to static friction in the case of rolling, but is this picture clear? These are the two differences or two things in this rotation and translation. Sorry if I'm repeating myself too many times, but there are two different levels of students like they need to hear this more than one time. So if you're rolling dot slipping, VCM matches omega r, ACM matches alpha r. If you're doing any general motion, these don't match. If you're rolling dot slipping, there is static friction. If you're doing any general motion, rotation and translations, it is kinetic friction. Any questions? Okay, there is a question, why does omega r go the other way of VCM? Just because of the spinning. Look at, like, it doesn't have to be, right? Like, to be honest, like, look at this example I'm putting here. VCM is going to the right. That's the translational motion going to the right. Omega here is clockwise. So if you follow this kind of omega around, this is the kind of sense of omega that goes spinning. So at this particular point that we're interested in, the contact point, the sense of spinning is to the left. That's the sense of spinning at this moment. So that's why, like, it came out here to be opposite to the sense of translation, right? So it's translating to the right, but the sense of spinning gives it a backward velocity, omega r. If it was spinning the other way, then the omega r will be the other way. But this comes from spinning. That's from the omega. Okay. So let's look at a problem here, and like, this is a very important, like, kind of topic. So it's fine to take our time here. So look at this problem from the practice that we did in week 15, day 1. Not all section got to this problem, but I think it's like, we've seen a variance of these problems many times before. So what is happening here? Well, there's an initial situation and there's a final situation. In the final situation, the question says, reaches rolling dot slipping. So at the end, if you leave this wheel going on for a little bit, eventually it will reach rolling dot slipping, which means initially it was not rolling dot slipping. And you can see that actually from the following fact. Initially, like, it was having zero velocity, it was not moving, it was not translating at all, and it was spinning into the page. Into the page means clockwise, by the way. It was spinning clockwise. So initially it was not, this is not rolling. It's very important to identify, is this rolling dot slipping or not? The initial situation is not. You're not translating at all, you're just spinning, just not rolling dot slipping. In the final situation, you're doing rolling dot slipping, and we're asking, basically the question is asking what is the final velocity at the end. So again, this is a different context. The problem we did was pulleys. This is not pulleys, but still thinking the same thing. Am I doing dynamics or am I doing conservation loss? That's the first question that comes to your mind. What determines that? What the question wants. What does the question want? Wants the final speed. Final speed is not a dynamical quantity necessarily. It's not an acceleration. The question doesn't care about the acceleration of the object in this stage. Doesn't care about what is the force. It could have asked you what is the static, like, kinetic friction force. Then that would have been a dynamics question. But doesn't want acceleration, doesn't want force, doesn't want the time. How much time does it take to reach rolling? That's a different question. Doesn't want that. So since the question doesn't care about A or force or time, then we shouldn't do dynamics. We should immediately think conservation. Something is conserved and we're going to use it. So that's like the game that we're playing. For every problem, we think about this. Do I have to use dynamics or can I get away with conservation? Here I can get away with conservation because I don't care about A's, accelerations. I don't care about a particular force. I don't care about the time. So now it's time to think about what is conserved. Is this clear about how we approach the problem? This is not dynamics. Like, no need for dynamics here, basically. Okay, so if we agree that we should be using something that's conserved, we have to decide what is conserved. So how do we deal with that? We draw the free body diagram. So in any case, you need the free body diagram of the object. If you're doing dynamics, you're doing for F equals ma, you have to see the forces and torques, etc. So you definitely need free body diagram for dynamics. But even for conservation, to determine what quantity is conserved, you need to see the free body diagram. So in any case, you will need to do the free body diagram. So let's do this free body diagram at a general point of motion. So this is how it looks. Again, we need to keep every force at exactly the location it is acting from. very important for understanding torques, okay? So gravity exists from the center of mass, not from any point. You have to put it at the center of mass. That's where gravity acts. So that's one force. There's normal force from the ground. So it's acting from the ground, like here. And then I'm drawing the free body diagram at a general point in between the initial and the final stage. So should I have kinetic friction or static friction? What do you think? Kinetic or static? Right. So I got like mixed responses, but which is fine. We're learning this, okay? We're like internalizing this. It's kinetic because we're not talking about the final state. It's only static at the very end because rolling without slipping, that's static. But like the problem doesn't talk about the very end alone. We're doing from the very beginning to the very end. So any point in between, you're not rolling without slipping yet. So you don't have static friction yet. So what I'm saying here, not rolling means kinetic friction, not static. We're not doing static unless if we're analyzing the rolling without slipping, which we're not doing that. We're doing from something that's not rolling without slipping until it reaches there. So anywhere in between, there is still kinetic friction. Still kinetic. So initially it was, let's look at what happens initially so that we know what direction of kinetic friction exists. Initially, let's do the initial, oops, no, come back. Okay. So initially this is a bad color. Let's do this. So V initial 0, like translation, it was not moving initially, but it had an omega. Omega initial is not 0. It was into the page. Into the page means clockwise. That's the convention from the right hand. Into the page is clockwise. Out of the page is counterclockwise. So the into the page here, the clockwise rotation looked like this. That's, sorry, oops, the other way. Clockwise is like this. That's omega. Okay. So that's like initially, like if we just look at the initial situation, there was this omega clockwise because clockwise is into the page, and there was no VCM. So if you analyze this situation right here, which is not rolling, not slipping, you will see that the contact point right here only has this backward spin omega r, V of the contact point. Let me call it P. So it has this backwards velocity from the spinning because the spinning happens clockwise. So this contact point is going to the back, to the left. That's why friction here is kinetic and forward. And like many students, when they did this in class, they were kind of confused. How come kinetic friction is forward? But that's the case. Kinetic friction doesn't care about anything except for the contact point. The contact point here was moving to the left, moving backward. Why? Because of the spin. The spin of omega clockwise makes it like move backwards. It's clockwise, so this contact point is kind of moving backwards. So that's why kinetic friction is against that forward. So that's the free body diagram. Gravity normal force, kinetic friction forwards. Any questions about why the force of friction is forwards? It's all about, again, if you're doing a general kind of motion, not rolling, not slipping, think about how the contact point is moving in total, in net, and oppose that. Here, the contact point was going backward from the spin, and that's it. It wasn't translating yet. So kinetic friction is against that, so it's forwards. Okay. All right, so let's write down now. Again, the big picture is what we found. We found the problem, and we realized all what we need is the final speed. So we don't have to use dynamics with it. It's not a dynamical quantity, not acceleration or force. So we decided we're going to use conservation of something. So now this, like, I want your thought process to go like this. Dynamics? No. Okay, so conservation. Conservation of what? Okay, let's do the free body diagram first. And then from that, look and figure out what is conserved. We have 3 options. The 3 options, you can have a case where all 3 are conserved. Energy, momentum, angular momentum. You can have a situation where only 1 is conserved or 2. you need everything that's conserved. If you have a situation where the three quantities are conserved, you will need to write the three of them. Like not one is just enough. So you need to go through the list, energy, momentum, angular momentum, and figure out what is conserved. So let's do that here and see how we do it. So we talk about, is energy conserved? Is linear momentum conserved? Is angular momentum conserved? Which ones are we using? Okay, that's just general approach. Let me silence my email. Okay, so we think about the three things. So energy, I want you to always have this big picture. When is energy conserved? When there is no, like, let's write down the condition. I need non-conservative work to be zero. That's the condition for using energy conservation. When is linear momentum conserved? I need the forces external to be zero, no external forces. And when is angular momentum conserved? I need to find the point. Angular momentum is like a little trickier than the others, because you need to find the point. Angular momentum is about a point in space. So we say angular momentum about a point S. So you need to find the point S such that there is no torque about this point. So these are the three conditions. So yeah, we'll talk about that. Okay, so these are the conditions. If non-conservative work is zero, energy is fine to use, conservation of energy. If external forces are zero, momentum is fine, is conserved. If you can find the point where torque is zero, angular momentum about that point is conserved. Okay, so we go through the list. Every time you decide not to use dynamics, which is a good thing, because if you're doing conservation, it's much easier, just like conservation of energy, one line, done. So if you're not doing dynamics, go through the list. Is energy conserved? Momentum, angular momentum. By the way, linear momentum P and angular momentum L are two separate ideas. Do not mix them, please. Some students think like this all momentum, so they write down like MVs together with MVR. No, they are different units, different ideas, separate ideas. Momentum and angular momentum, don't mix them in the same equation, separate equations, okay? Okay, so let's go through this. Non-conservative work. What's non-conservative work? Non-conservative work in 90% of situations is kinetic friction. The main force that dissipates energy, that creates non-conservative work, is friction, kinetic friction, not static. So the question about is non-conservative work zero or not usually is about, do I have kinetic friction or not? That's usually the question. And here we do have kinetic friction. So it was important to realize that we have kinetic friction here. As this is going forward, there is kinetic friction forward because the contact point is not addressed. So we cannot use this because Fk is like the main force that creates non-conservative work. So energy is not conservative. The force of kinetic friction dissipates energy. It's a non-conservative work. So it's not energy. We're not using energy. Is this clear? Any questions? If it was static friction, would have been okay. Static friction doesn't create any work because static friction is, by definition, it means there is no distance. Like kinetic friction, you have to have two surfaces that do this, slide on each other. That's kinetic friction, dissipates heat. Static friction means you're just static like this, so it doesn't create work. Even if this was rolling, it's kind of like resting on the surface like this, that's not work. I need to have sliding to have work. So moral of the story, if you have kinetic friction, energy is not conserved. We have static friction in any situation. Static friction is fine. Static friction conserves energy. It doesn't do any work. Okay, so rolling without slipping, energy is conserved because of static friction. Okay. Any question about energy conservation here? We cannot use it because there is kinetic friction which dissipates energy, which is a non-conservative force. Okay, so we go to the second. Is external force zero? Okay, let's look in the X direction. If we call X and Y, the Y direction, the forces cancel, the gravity and normal force cancel. But in the X direction, you only have the force of friction. There's no other forces. So again, this is not true. Like F net in X is not zero. You do have an net force, like it's again the kinetic friction that's creating trouble here. So kinetic friction dissipates energy, so cannot use energy. And kinetic friction is an external force to the system, to my ball, to my sphere. So cannot use momentum. Momentum is changing. And you can see momentum, linear momentum is just mv, okay? That's linear momentum. So linear momentum is definitely not conserved because you start from rest and you end up moving, right? It starts from mv being 0 and it's gonna like translate at the end. So momentum is not conserved. Why? Because there is an external force which accelerates it. Any questions? So we see now that the free body diagram, having it correctly, allows us to think, is energy conserved, is linear momentum conserved, angular momentum conserved. And we see in this particular situation that kinetic friction did not allow energy to be conserved and did not allow momentum, linear momentum to be conserved. So our last resort, okay, can you explain again why there is external force? All the forces in the free body diagram are external, by the way. Like we call external, meaning outside of my actual interests, object of interest. Like my object of interest here is the sphere, it's the wheel, okay? So friction is an external force to it. Gravity is external, normal force coming from outside, coming from the ground. That's an external force. So for linear momentum to be conserved, we're hoping that there are no external, like nothing in the free body diagram, or like all the forces in the free body diagram cancel out. That's our hope for linear momentum to be conserved. We hope that the forces that show up in the free body diagram cancel out. But this is not the case. Whenever there's friction, does it mean we cannot use conservation of momentum? Well, I can't really say a general statement like that because you can have friction canceled by other force. If there exists some force that somehow cancels friction, then there will be no net force and momentum will be fine, okay? So it's just all about, do the forces cancel out, all of them, on the object or no? If the forces cancel out, then momentum is conserved in that direction. But here, there is nothing canceling friction. Okay, any other questions? Okay, so about angular momentum, we are looking, this is our last resort. We're not doing dynamics, we're not doing energy, we're not doing momentum, so it has to be angular momentum now. So angular momentum, you need to think about the space that you have and find the point in that space. You need to figure out the point yourself. Where these forces that in the free body diagram, by the way, I'm gonna like remove the omega r so that you're not confusing this as a force. It's not a force. Okay, omega r is the speed. So this is a free body diagram right here. That's it. Okay, like omega r is the speed, not the force. This is a free body diagram. I just wanted to show you that omega r is to the left, so friction is to the right. So looking at these forces right now here, we want to find a point in space, some point wherever it is, such that these forces in the free body diagram, the torque from them cancels out. Okay, so let's take some example point. Let's look for some points. Let's, for example, take center of mass. That's a point in space, center of mass here. So looking at this diagram here, is there a torque about center of mass or no? From the forces, like you see this forces, we only have three forces, mg, normal force, friction force, forward. These forces, do we have a net torque about center of mass or no? Yes, yes, we do, right? Because of the force of kinetic friction. Look at the force of kinetic friction. Like this is your object and kinetic friction is like pointing like this, center of mass is right here. So there is a perpendicular distance, force times a perpendicular distance. So it's trying to make it rotate this way. So kinetic friction does create torque about center of mass. So it's not, we cannot say angular momentum about center of mass is conserved. Like yes, gravity doesn't create torque about center of mass. Normal force doesn't create torque about center of mass because like parallel to, but friction does. So that's not a good point. Angular momentum about center of mass is not conserved. So we need another point. We need to figure out maybe there is another point. But any questions about this kind of center of mass situation? Okay, so that's why we used like this problem showed up like more than one time, like in different places in the course. And every time we saw it, we basically said, okay, if you pick any point on the ground, then there is no torque about this point. That's the point that we're looking for. Why? Like, let's take a point here, point S, called S, somewhere on the ground. Why do we pick it? Why did we pick it on the ground? Because kinetic friction then will not create torque, because it's parallel. Again, torque is what? It is force and perpendicular distance, or like R cross F. The R vector from this point to the force is like this. So the position vector, the R vector from the point S to the friction force is exactly in the same direction as the force itself. There's no cross product here. R cross F is 0. In other words, if you have a pivot, if you have like an object and you pivot it from some point, you pivot it from here. And if you push parallel to that pivot, it never rotates. You need to push perpendicular. That's where it rotates. If you have a pivot, if you have a point you're thinking about, and if you push with a force parallel to it, it doesn't create torque, doesn't rotate. You need to push perpendicularly to it. So that's the situation here. That's why we picked this point on the ground, because the kinetic friction force does not do torque there, because it's parallel to it. You're pushing at the pivots. It's like doesn't rotate. You have to push perpendicular to the pivot to create torque. That's why in this scenario here, we say only if we think about the point S, which is on the ground, that's conserved. That is what we're using this point. Okay, what about mg and normal force? You had a p-set problem like this, right? You had to explain that in a p-set problem, if I remember correctly, right? So there is gravity and normal force, both of them create torque, but they cancel out, because the torque from mg and torque from normal force have opposite directions and have the same perpendicular distance. Look at this. The perpendicular distance from gravity to the point S is this. This is the perpendicular distance, perpendicular to the force. This is the distance perpendicular to mg. For the normal force, this is also the perpendicular distance, exactly the same, perpendicular to m. So the torques created by gravity and normal force cancel out. So you don't have to worry about that. You have to only worry about kinetic friction. And now picking a point on the ground, kinetic friction is parallel to it, doesn't create torque. It needs to be perpendicular to it to create torque, to create a rotation. Parallel to it, if you push to the pivot or like pull from it, doesn't rotate. The object doesn't rotate. You need to push perpendicularly. So all in all, there is no net torque about point S, because the kinetic friction force is parallel to it, and the torques from gravity and normal force cancel out. Okay, question here. 1 second. Okay, there's a good question here. Okay, what if we pick the point of contact, like the point of the wheel contacting the ground? The thing is, we need to pick a general point, because this is like traveling, and we want some point where angular momentum is conserved during the whole stage. Remember, we start from some place not rolling without slipping. It goes a little bit until at the end it rolls without slipping. The contact point doesn't remain a contact point forever. It keeps changing. So that's why we pick a general point, so that we want to make sure that about this general point throughout this whole journey, angular momentum remains constant. If you pick the contact point of the wheel right now, it's going to leave it next, and now it's going to be like left behind. So you want to make sure that when it is left behind, it still conserves angular momentum, if that makes sense. So that's why we pick a general point on the ground, because that represents a general case that is true throughout the whole journey. Okay, so that is the problem-solving mentality I want you to have for the final exam. Dynamics, do I want acceleration or force, or simple harmonic motion or circular motion? As I told you at the beginning, simple harmonic motion, circular motion is dynamics, because you want to use the acceleration. If I don't want to do any of that and just find the final speed like here, you think what's conserved? How do we know what's conserved? Draw the free body diagram first, and then go into the three things. Energy conserved if there is no non-conservative work, like no kinetic friction, basically. Momentum is conserved if all the external forces cancel out in the x direction, for example, like in the particular direction. And angular momentum is conserved about a point if there is no torque, if you can find the point in space where the torques cancel. And we found this point here, a point on the ground. So now let's solve this problem. This was all about how do we approach it. Now we know what to do. We are trying to write down conservation of angular momentum about the point on the ground. So now let's just solve it. So the initial situation versus the final situation. So initially V was 0 and omega was clockwise, omega initial. Finally, it's gonna roll without slipping. So there's some V final and omega final. But don't forget that V final is just omega final R, because finally this is rolling without slipping. So omega final and V final are not like just random independent quantities. They are related by the rolling without slipping condition. So what did we decide to do? We decided to do conservation of angular momentum about the point here. Okay, so now let's see what we do to calculate angular momentum. And this is an important idea. Angular momentum has two different forms, has two different ways of like writing. There is I omega. So I omega is a form of angular momentum. And there is MVR, like R cross MV. That's another form of angular momentum. If you go up like here in these notes, you will find in the table I wrote the general problem solving strategy here. I wrote down how to write energy, how to write momentum, how to write angular momentum. So for energy, don't forget, again, we're dealing now with a situation where the object is both translating and rotating at the same time, okay? So if you're doing rotation and translation at the same time, don't forget that you have two kinetic energies. 1/2 mv squared from the translation, plus 1/2 I omega squared from the rotation, from the spin. That's for energy. Don't forget the two types of kinetic energy in rotations plus translations. Similar to that, angular momentum. Angular momentum down here has two different types. Let me write it here. This part, the R cross MVCM, this is a translational part. If the object, if the center of mass is translating, it's basically like a point mass translating. So it creates an angular momentum about a point which is MVR perpendicular. Like the magnitude of this guy here is MVR perp. That's the magnitude of this cross product here. That's one form of angular momentum. If you're translating, there is MVR. And if you're spinning, there's I omega. That's the rotational angular momentum. So please don't forget this. If you're doing energy, again, the 1/2 mv squared is translational. The 1/2 I omega squared is rotational. So if you're doing both rotations and translations, don't forget that you have two different energies, kinetic energies, and then you have two different angular momentum. Okay, linear momentum is good. Like if you're using linear momentum, just MVCM. Doesn't care about the rotations. Linear momentum is all about the translation. But kinetic energy has rotation and translation terms. Angular momentum has rotation and translation. So let's apply this to our situation here. So we're calculating angular momentum at the beginning and at the end, and we're equating them because it's conserved. So angular momentum at the beginning did not have any translational part because V was 0. Just purely rotating, so it's just I omega. That's the initial angular momentum in magnitude. If you want to write it as a vector, this is in k hat. Depending on the choice of k hat, I'm going to choose k hat into the page here. So this is into the page, this is k hat. As a vector, it's in k hat. That's the initial angular momentum, I omega. I didn't have any MVR or like R cross MV because there was no V initially. Then when you go to the final situation, now you have both. So you have I omega, so ICM omega final. I'm going to write omega final as V final over R. This is just omega. I know that from rolling without slipping. That's the I omega term. And I also have an MVR perpendicular term. So the center of mass right here is moving with velocity V final at the distance, perpendicular distance from the ground R. Again, don't forget, we're calculating it about the ground, a point on the ground. The perpendicular distance from the ground is R. That's why the second term is just MVR. This whole thing is like in K hat. So that's it. You set them equal. solve for VR, you're done. So like literally the solving of the problem is just like one line. I omega is I omega plus MVR, done. That's like the whole solution. And then using V equals omega R. But like getting there, thinking about what to choose, this is not dynamics, it's a conservation, okay, conservation of what, like that's the thought process that goes here. Any questions about this type of problem? And through this problem, we showed that kinetic friction exists. If you're not rolling, not slipping, then it's kinetic friction. And the way to determine the direction of kinetic friction is to just look at how the contact point is moving and oppose that with kinetic friction. Sure, okay. Okay, so what's the MVR? Okay. So the mathematical way of doing this is like this. There's VCM, and there's omega final, and the point S is like right here. So if you want to do this like purely mathematically with a cross product, you will say the following. There is a vector R coming from the point S to the center of mass. And then the angular momentum is I omega, okay, so that's one term. And the second term is R cross M VCM. That's like the translational type of angular momentum. So the MVR I wrote there is coming from here. If you want to do it mathematically, you do this cross product. Just answering this question, other question quickly, because initially we were told the velocity was 0. We didn't have any translation of it. The initial situation in this problem, V was 0. So we don't have MVR initial. V was 0. Okay. So doing this cross product right here, like if you want to do it, like you can write down the components of R, cross the component of velocity, but like the way I think about it is like this. I don't care the cross product whenever you're doing a cross between two vectors. It just means that you're getting the perpendicular part of one into the other. You don't care about the vector, the full vector R, you just care about the perpendicular part of it, perpendicular to what? To V here. Like this velocity vector, I'm gonna keep it as it is. And then for the R vector, there is part of it that is parallel, this part right here. That's parallel to V. I don't care about that. I only care about this. That's R perpendicular. Perpendicular to what again? To V. So when you perform this cross product, you will find that it just matters this perpendicular distance, which is RMV. That's where it came from. So MVR is used for both point masses and for, yes, yes. Okay. MVR is like, yeah, MVR is coming from translational motion of a point mass. The center of mass here acts as a point mass. So that's why for the translational motion, we can just sort of reduce this to a point mass translating. That's why it's like MVR. So yes, it is equivalent to a point mass translating, but don't forget to add the I omega of spinning. How can you tell the initial angular momentum was found with a point S? Ah, good point. Okay, okay. Okay, many questions here. So let me answer the question about I omega. The I omega term doesn't matter where the point is. And this like has like a big derivation. But yeah, the point S only matters when you're doing the translational part. The I omega is ICM omega. And like, if you want a quick way to say this, like why this term right here doesn't depend what point you're calculating about, because we're splitting the motion of the object into translation of center of mass and rotation about the center of mass. So these two terms come from this. ICM omega is the rotation about center of mass. So it's all about center of mass, this first term, ICM omega. Because I split the motion into center of mass is moving, and at the same time there is spinning about the center of mass. So center of mass moving part will care about the points. Like now it's like MVR perpendicular. That part will depend on the point. But the I omega is always about center of mass. And you can prove that mathematically, but that's how we think about angular momentum. ICM omega, that doesn't depend on what points you're calculating about. And then the MVCM will carry the thing. Okay, so about the cross product, I define K hat here to be into the page. So I don't know if that answers your question, but like R cross MV here is kind of, yeah, you need, I try to avoid cross products a little bit because you need, if you want to do it mathematically with like, sorry, with your hand or something, you need to put them tail to tail. Like this is a vector R, there's a vector V, going from R to V is clockwise. Like that's one way to do cross products, R cross V. So you put your hand with R, you rotate it towards the second vector V that crosses into the page. So it's positive. So I kind of try to avoid thinking about cross products much. Okay, so there's a question about why did we pick the ground? We were just like talking about this for a while before that, but if you pick the center of mass, let me just repeat this quickly. This is a free body diagram. There's a force of friction on the ground pointing to the right. If you pick center of mass, this kinetic friction creates torque about it. There's perpendicular distance to center of mass. So that's why the net torque about center of mass here is not zero, because friction creates torque about it. So angular momentum about center of mass was not considered. But if you pick the ground, then the friction force doesn't create torque. There's parallel to it. That's why we picked the point on the ground, so that the kinetic friction does not create torque right there. That's why angular momentum there, only this point on the ground, angular momentum is conserved about. So yes, if it was moving the other way, I would have said minus K hat. So how do I determine? So there are two ways of like figuring out directions here, positive or negative K hat. The mathematical way is to write down the cross product like here and like try to evaluate the cross. Okay, that's one way to do it. Write down the vectors R and MV and do the cross product. The other way, which is like what I basically use, is just I try to think of the sense of rotation again. Okay, I kind of talked about this with torques. I try to think about the sense of rotation that this motion is making about the point. I am moving to the right. Do you see this like pointing to the right, or is it flipped for you? Is this right? Okay, so to the right, and the point is on the ground here. So moving to the right about the ground is kind of like making a clockwise sense of rotation. Like the motion thinks the motion to the right here, and the point is on the ground. So moving to the right, it looks like as if I'm rotating about the ground clockwise. That's why all of these terms are clockwise. The omegas are given to be clockwise, and even the MVR sense of rotation is clockwise because you're moving to the right, and the point is down here. So the sense of rotation is kind of clockwise for me. That's how I figure out the direction of angular momentum without crosses. Here, let's just see another question. The formula of angular momentum usually R equals MV equals I omega. No. It's not the formula. No, you got it like what you're writing down is a special case like with the question. Angular momentum is both I omega and MVR. That's a general case. So here, because if you're translating, there is MVR, like R cross MV. And if you're rotating, there's I omega. So here in these examples where you're translating and rotating, both these exist. Both are angular momentum. So in that case right here, the initial one just had I omega because it was just spinning, not translating. And the final one has both types because it's both translating and rotating. Yes, if you had VF here to be to the other way, then it will be negative because that's a counterclockwise sense of rotation. Yeah. So yeah, please remember this angular momentum in any general case has two terms, MVR and I omega. If you're translating MVR and if you're rotating I omega. And yeah, so initial here it was just I omega, final there's I omega and there's also MVR, and it's like both of them are kind of in a clockwise sense about the ground. Or you can perform the actual cross product. You can find the solution on the MITx. It is doing the cross products. If you want to see the mathematical cross product here, you want to use that, the solution on MITx for this problem, which is on week 15, day 1 problem. But the way I think about it is the magnitude of angular momentum is MVR perpendicular, and the perpendicular distance is just the radius. This is perpendicular here. The magnitude is MVR perp. And the direction is from the sense of rotation about the point. Sense of rotation here, if I'm moving, the point is on the ground here, I'm moving to the right. So this kind of sense of rotation, like motion, is kind of like going this way above the ground, clockwise above the ground. So it's also clockwise, just like omegas. And I define clockwise to be positive. If you want to do the cross product, look at the solution on MITx. So yeah, angular momentum has two terms generally, I omega from rotation and the R from translation. And then this is conservation of angular momentum. I omega initial is I omega final plus MVR final. Any questions? Okay, so let's recap and see what we're talking about here. We're talking about rotation and translations. And I said there are two different things happening here. General kind of motion, which is called slipping or skidding. Don't care about the names again. But this general kind of motion, you're translating one way and you're rotating in any other way. Like the VCM is not necessarily omega R. In that case, the contact point is moving relative to ground, so there is kinetic friction. But if you're rolling without slipping, G hat is into the board means G I hat is to the right and G hat is down. G final is positive, I hat. R perpendicular is negative, J hat. No, R is up, yeah, because we're doing R cross V. So negative J cross I is actually positive K. I cross J is K. So J cross I is negative K. So negative J cross I is negative, is positive K. I hope that makes sense to you. I think you can easily like find a minus sign when you're doing crosses. That's why my personal preference is just to think about senses of rotation from the velocity about the point, but it's not like favorable for everyone. So anyway, coming back to the big picture right here, rolling without slipping is a special case where the contact point is exactly at rest because the VCM and omega R at the bottom cancel exactly. So the contact point is always at rest in rolling without slipping, which means that we have static friction. Don't forget this. Question says this is rolling without slipping, add static friction to the free body diagram. Okay, which way do we add it? Let's think about that now. It's like a heavy kind of idea. So please refresh, focus. We talked about direction of kinetic friction in the general case. Just oppose the motion of the contact point. Like here, the contact point was moving net to the right because omega R here was bigger than VCM. So kinetic friction is just against it. Static friction in rolling without slipping is trickier because the contact point is not moving. There is nothing to oppose. Right? It's not moving to the right or to the left, the contact point in rolling. So there is nothing to oppose there. So how do we put static friction? So let's do that, okay? Please, energy, focus. So I'm gonna do that in the context of the harmonic oscillator problem. And from that, I'm gonna, like, after we finish talking about static friction and rolling, I will go into simple harmonic motion. That's like a segue between the two things. Okay, so I'm gonna review harmonic motion. Don't worry in like after we finish static friction part. But this is the problem right here, which is a harmonic motion part. How do we know it's a harmonic motion? The question will tell you. Like, for example, here, what is the period of the simple harmonic motion? So it's a simple harmonic motion. Simple harmonic motion, the main thing you're trying to do, I'm gonna discuss that, is find the acceleration of the object. That's basically what you're doing. And if you're doing things correctly, the acceleration will turn out to be minus a constant times a position. That's what you're trying to do. So what I'm saying is simple harmonic motion should always come to dynamics because you're trying to find the acceleration. You're trying to find A is minus Cx or alpha is minus C theta. That's what you're trying to do. So I know that the solution for this problem on MITx uses energy, which is kind of confusing to you. Some of you told me because you have never seen that before. And like, yes, I don't want you to think about different approaches. Usually before this year, we did this energy approach in class, but we didn't get to do that this year. We didn't do the energy approach for harmonic motion. So I want you to just like systematically think about harmonic motion with energy. Sorry, with dynamics. Okay, so harmonic motion means F equals ma, torque equals I alpha. Figure out the acceleration. because that's the proof of harmonic oscillations. So that's the first part. We know we're using dynamics here because it's a simple harmonic motion problem, and simple harmonic motion is all about the acceleration. Okay, so we're doing dynamics. So that's the first thing. Dynamics with conservation. No, we're doing dynamics because it's harmonic motion. So the next question is, okay, we're doing dynamics. What do we do? Well, free body diagram. First thing, free body diagram. The first thing we do. So let's do that. I'm gonna worry about the harmonic motion part later. It's more here about static friction because the question mentions here that this is rolling, not slipping. It does mention that. Let's find it. It can roll without slipping. It is rolling without slipping. So even if the question here doesn't mention static friction in any way, doesn't mention it. But you have to realize that rolling without slipping, if you're doing a free body diagram for it, then you have to include static friction. So let's do that. So here is how it looks. This is your sphere, distance x, and my coordinate system is I hat and k hats into the bridge. So let's do the free body diagram. And this is rolling, like the question says rolling without slipping. So that means static friction, static friction. Okay? Don't forget this, you have to remember. Even if the question doesn't mention static friction, you have to remember. Rolling means you put static friction. Any other general motion, it is kinetic friction. Okay, so let's do the free body diagram. So we have the usual mg from the center of mass. You have the normal force from the ground. Again, put every force exactly where it is acting. Gravity from center of mass, normal force from the ground. We have a spring force here because the spring is connected to it, and the spring is connected right here. This is where the spring is acting to the right. And since this is the equilibrium position right here, the spring force, like remember this, the spring force always pushes towards equilibrium. It wants you to go back to equilibrium. That's what the spring force is. The spring force here is towards equilibrium, so it is to the left. So this is the spring, F spring. Okay. Any questions so far about the free body diagram? Usual gravity from center of mass, normal force from the contact point, spring from the spring pointing towards equilibrium. So there is static friction, as we said. But which way, right or left, we have to think about this. So what I want you to think about right here is, at this moment right here, at this moment, at this instant of time, is the wheel accelerating linearly, like translational wise? Is this guy translating with ACM? If there's an ACM at this point, is it to the right or to the left? What do you think? ACM, center of mass translation, accelerating right or accelerating to the left at this instance? Are you with me? Okay. Yes. Yes. So this question is very crucial for finding static friction. So if you look at the free body diagram right now without static friction, horizontally you only have the spring force pushing it back to equilibrium to the left. So the center of mass is going to accelerate to the left. There is ACM at this point to the left. Yeah, towards equilibrium to the left. Right? And that's the behavior of a harmonic oscillator, by the way. The acceleration is always towards equilibrium, right? That's the meaning of restoring force, harmonic oscillation. Harmonic oscillations mean you're always accelerating towards the equilibrium. If you're on this side, equilibrium is here. If you're here, you're accelerating towards it. If you're there, you're accelerating towards it. So you're accelerating ACM, right? Okay, and then don't we know that rolling without slipping mean that ACM is alpha R? We know that. So if there is ACM, if center of mass is accelerating translationally, then there has to be an alpha. It has to also be rotating, accelerating rotationally with alpha. Agreed? Rolling without slipping means translations and rotations are matching, are in sync. At this moment, it is accelerating to the left because of simple harmonic motions pushed back to equilibrium. So there must be a following alpha. For rolling without slipping, they have to match. So there is an alpha in the same orientation. But look at the free body diagram right now and tell me what is the torque, what force so far is creating torque about center of mass. Like for alpha to exist, there must be a net torque about center of mass because torque is I alpha. Torque Cm is I alpha. Okay, so if you look at the spring force, it is actually pointing towards the center. The center of mass is like where, it's right here, that's center of mass. Yeah. So look at these forces right now, like, yeah, static friction, you're right. But like without putting static friction for yet, none of these forces create torque about center of mass. I hope that you can see that. If you don't see it, please ask. You can ask in private, okay? Normal force doesn't create torque about center of mass because like parallel to it. Again, if you have a point and if you push towards it, that doesn't create torque. You need to push perpendicular to it, not parallel to it. So the normal force doesn't create torque about center of mass. Gravity doesn't because it's acting right there. There's no distance. Torque is force times distance. Gravity doesn't have a distance from center of mass. Gravity doesn't create torque. Normal force doesn't create torque about center of mass. Spring force doesn't create torque as well because parallel. It's pushing like this, parallel to the center of mass. It's not creating torque. Can everyone see that? At this point, with the forces I put on the diagram here, there is no torque about center of mass. Any questions about that? So that's the key idea right here. In rolling without slipping, static friction main job, the job of static friction mainly is to supply the torque. Because usually there will be no other torques. Sometimes there are, but still static friction the main job of static friction in rolling without slipping is supplying the torque needed for rolling without slipping to keep happening. So that's how we know the direction of static friction in rolling without slipping. So let me tell you this, static friction that's like generally correct, responsible for creating the torque and alpha. Creating torque Cm and hence the alpha that is needed for rolling. So I'm gonna go back to my table for rolling versus general just to put this there. So how do we know the direction of static friction from the direction of the needed torque? It responsible, the static friction force in rolling is responsible for creating torque and alpha to match ACM. That's how we figure out the direction of static friction. So I'm going to show you how. Yes, the private question, yes. So again, at this point in the free body diagram, there is nothing creating torque, but I know there must be torque about center of mass because this is rolling without slipping and it is accelerating backward to the left. So alpha has to match. So this is the process that goes into your mind when you're thinking about the direction of static friction and roll. You say, okay, where is ACM? Not VCM. It's all about acceleration, alpha and A. So where is ACM? Well, in this example right here, it's accelerating to equilibrium. So ACM is to the left. So where is alpha? Alpha has to match because it's rolling without slipping. If you're translating one way, you have to rotate in the same way. So if ACM is to the left, alpha has to follow in this orientation. The spring force doesn't exert torque about center of mass because it's like right straight acting, like it's parallel to it. Just like the normal force, for the same reason that the normal force doesn't. Normal force is like parallel to the radius. The spring force is also parallel to the radius. If you don't understand this, ask again and I will explain more. So I'm saying ACM is to the left because you're accelerating towards equilibrium. So alpha has to follow. From rolling without slipping, they have to go hand in hand. So if you're accelerating to the left, you have to be alpha, doing an alpha to the left as well. So it's like counterclockwise here. Do you see that? So there has to be net torque in the same direction as this alpha. So now you tell me, to generate this alpha in this particular orientation, which is counterclockwise, do I need static friction to be to the right or to the left? Again, the way I think about directions of torque is just kind of the sense of rotation that this force is trying to create about center of mass. This is center of mass right here. Yeah. Think about it. It is to the right. To the right. Again, like I don't know, this is how I think about rotational quantities. I try to think about how they make the object want to rotate. So so I'm saying this guy is accelerating with ACM to the left. So it has to have an alpha like in this same orientation here. So the only force creating torque about center of mass is static friction from the ground here. If static friction is to the right, then the sense of rotation is trying to create about center of mass is like this. Like follow the static friction force about center of mass, trying to rotate it this way. That's what I want. If it was like, if static friction was going the other way like this, it wants to rotate it that the opposite way, which is not what I want. So this is static friction because I need alpha matching ACM to the left, alpha also kind of to the left, which is counterclockwise. So I need this static friction direction so that I create torque this way. Okay, so that's how we figure out, that's the general way of thinking about static friction in rolling dot slipping. What is the direction of alpha in the problem? And hence, how can I put a static friction to create that alpha? So in that particular problem, static friction is to the right. So it's like a little bit challenging, but just practice on it and you will feel better. So again, just to summarize here, direction of static friction. We said ACM is to the left, like negative I hat. So alpha has to be counterclockwise, which is negative K hat. In this situation right here, K hat is defined into the page. So alpha is like out of the page, like counterclockwise out of the page. So as alpha is out of the page, I need torque about center of mass to be out of the page, to be counterclockwise. And so that's why static friction has to be in positive I hat, so that it pushes it in the sense of alpha that I need. That's static friction. And now we've completed our free body diagram. So spring force towards equilibrium, gravity normal force as usual, and static friction in this orientation just to make the necessary alpha for rolling dot slipping. Now we can move on with like the problem, but this is the static friction direction. Any questions about this example? So please don't mix the kinetic friction that is in the general kind of translation and rotations versus the static friction, which is only in rolling dot slipping. Rolling dot slipping means static friction to supply alpha that is needed. Any other general kind of motion, the contact point will be moving relative to ground, so just oppose it with kinetic friction. Okay, we're calculating torque about center of mass. The normal force, if you want to do R cross F, the R vector is like this to the normal force. From center of mass to the normal force, that's R. So R cross F is 0 because it's kind of anti-parallel. That's why the torque from normal force and from the spring force also is 0. Any force that is parallel to the pivot, this is the pivot like center of mass, if it's parallel to it, like pushing towards it or like this, doesn't create torque about it. Mathematically, this is saying R cross F is 0. R cross F is 0. Yeah. Okay. Any questions about the direction of static friction and rolling? Let me remind you, of the examples we did in class. So we did, like when we did rolling without slipping in class, we looked at this kind of idea of static friction supplying the torque in two concept questions. Let me remind you of them. So you see the same idea. So we did it for the rolling down an inclined plane. Let me just remind you of this case. If you have rolling down an inclined plane, so rolling down, okay? So again, you ask yourself, where is ACM? Is this object accelerating translationally? Yes, it's accelerating down, ACM down, it's going down. So which way? Okay, sorry, let's do the free body diagram first. To the normal force, there's gravity, that's it. So far, again, without static friction, there is nothing creating torque about center of mass, same reason. Neither gravity nor normal force here create torque about center of mass. So static friction comes in and say, okay, I am here to help rolling happen, to make rolling happen. How? By supplying alpha matching A. A is alpha R. So since A is down, alpha has to follow like in a down sense, in a clockwise sense in this problem. You have to follow. Rolling without slipping means they go hand in hand. You translate and rotate together. So ACM is down, alpha is down, like in a clockwise sense. And so static friction has to be up the inclined plane because that is the sense, that's the direction that creates this clockwise rotation. It has to be pushing backward, was creating a clockwise rotation of the center of mass. So that makes sense. That was another example of calculating static friction direction during rolling without slipping. And then we did in class the other case where this thing is rolling up the incline. It's the same thing, but it's going up. And to your surprise in class, if you remember, static friction remained up as well. Because even if you're rolling up the inclined plane, you're still accelerating downwards. That was the problem in class. Whether the wheel is going up the incline or going down the incline, that's VCM going up or VCM going down. We don't care about the VCM. It's all about ACM, the acceleration of center of mass. That's what alpha matches and the torque matches. So both ways, ACM is down. Whether you're going down or going up, you're still accelerating down. Meaning that, like, even if you're going up, you're slowing down. Why are you slowing down? Because the acceleration, gravity is pushing you down. So in both cases, whether you were rolling down or rolling up the inclined plane, ACM was down, and so alpha is clockwise, so static friction was up. And that we did that in week 10, something like that in class. That's the same idea I'm talking about here. In rolling without slipping, to find direction of static friction, just find alpha, where alpha should be to match, to follow A. So start by thinking, where is ACM? Match alpha to it, needed for rolling without slipping. Then you can see which way static friction should point to create that alpha. So here static friction has to go up to create the alpha clockwise about center of mass. Any questions about this in-class problem? Okay, so that's our last nail into translation and rotation, which is kind of summarized here again. So either rolling without slipping, yeah, go ahead and write the question. Rolling without slipping, VCM is omega R and ACM is alpha R, very special case, translation and rotations match. General kind of motion, translation doesn't match rotations. In that case, kinetic friction exists at the bottom because the point at the bottom is not at rest, it's moving. But in rolling without slipping, the point at the bottom is exactly at rest. So you have static friction in there. And to figure out the direction, you just think about alpha. Where is alpha? That gives you the necessary direction for static friction. It does. Let's see. Are you talking about rolling up the inclined plane? So VCM is up, like it's speeding, like it's moving up. That's VCM. But it's still accelerating down because there's still force of gravity slowing it down. The acceleration is not the same as velocity. Velocity is the way that you move. I'm moving like this. Acceleration is how the velocity is changing. So yes, I'm moving up, but I'm slowing down. Slowing down means that the acceleration is the other way. This is coming from gravity. Whether you go up the incline or you go down the incline, gravity pulls you down. The acceleration is always down. Yes, yes, omega will be opposite to alpha, yes. Exactly, because omega is the speed, the velocity. But it's all, the torque and static friction is all about accelerations. ACM, down, alpha matching that, so clockwise. So static friction creates that. Otherwise, like without static friction, it wouldn't roll without slipping. It wouldn't rotate at all, which is not rolling. Okay. All right. So by the way, I'm gonna, yeah, on the inclined plane, the acceleration is always down. Yes, on the inclined plane because gravity is pushing you down. So this session is gonna extend till 5:30 or something like that. I have to get my daughter from daycare before 6. So it has to end like somewhere before 6, like before 5:45 or something. But yeah, I'm estimating like 5:30. All right, so next kind of big idea is simple harmonic motion. We kind of covered the general problem solving strategy, dynamics versus conservation. We applied that to pulley problems, we applied that to rolling without slipping, and in general rotation and translations, like something rotating and translating at the same time. The next big idea is simple harmonic motion, which we covered before for the first exam, but now we're back thinking about it. So we started the problem about harmonic motion, but I just took it as a chance to explain static friction. So now let's look at the harmonic motion part of it. So what's harmonic motion again? Simple harmonic motion is an oscillation. There is an oscillator. And I have this kind of summary slide here. So simple harmonic motion means you have an equilibrium position, equilibrium point, and then the object is going to oscillate about it. Some force is there, some restoring force is always trying to push it to equilibrium, so it's gonna just oscillate about the equilibrium. But now we have dealt with different types of motion in this course, so the oscillation can happen either linearly, like in X, you're oscillating in X, or like in Y. That's a linear oscillation. Okay, 1 second.
This is no problem. All right, I have a tip for her. I didn't put this on the deck. That was great. Thank you so much.
All righty. Sorry about that. All right, so simple harmonic motion, you have an oscillation happening. This oscillation can be happening linearly, like in X or in Y. That's usually when you have a spring. A spring makes you oscillate horizontally or vertically, like linearly. Another kind of oscillation is angular oscillation, like the pendulum. So you've seen both of them in the class so far, right? So you can have a pendulum, that's an oscillation in angle. The angle is oscillating. Or you can have a linear oscillation. So the idea here is if you're oscillating linearly, you want to find the linear acceleration A and show like your main target, like, trust me, your main target in any harmonic oscillator problem is to prove that this is the harmonic oscillator. To show me that this obeys the harmonic oscillator equation. How do you do that? Well, if you're oscillating linearly, you need to find the acceleration. This guy right here is just the acceleration. It's exactly the acceleration in X, right? So you need to find the acceleration of the object and show that it is equal to minus a constant times X. Like write it in this form. Second time derivative of X is minus some constant times X. If you do that, then you've showed that this is a harmonic oscillator. On the other hand, if the oscillation is happening in angle, like the pendulum, then you want to use alpha. You want to find the oscillation in the angle, so you're talking about alpha, the second time derivative of the angle, okay? And again, you want to show that alpha, the second time derivative of theta, is minus a constant times theta. That's what you want to show in a pendulum versus the linear oscillation. So that's why if you're doing a simple harmonic motion that's linear, you just write down F equals ma, because you want to find A. You want to find A, you want to find that A is minus Cx, you want to prove that. So you just write down F equals MA and find the A, and like hopefully it will look like that. That's for the linear oscillation. If you have an angular oscillation, like the problem that you just did in the P set, this last P set was the accelerating frame, the pendulum there. What did you do? You did the torque. If you, like the question said, using the torque method to find, like show that it's harmonic oscillator or something. Why did we use torque? Because we wanted alpha. Like for an angular oscillation, we want alpha. We want to find that alpha, prove that alpha, the second time derivative of the angle is just minus constant times the angle. So for that, we use torque. So I want you to keep that in mind. Okay. If you're oscillating linearly, you need F, just F equals MA will be in. If you're oscillating angularly, you write torque equals I alpha. Torque about what? Torque about the pivot, by the way. Like in this kind of problem, this is about the pivot point of the oscillation. Okay, so that's why that's how you approach a harmonic oscillator problem. Linear oscillation F equals MA, angular oscillation torque equals I alpha. Like that's it. And then work through the algebra and show that, okay, if it's A, it's minus Cx. If it's alpha, it's minus C theta. This C can be anything, just a constant in the problem. And once you write down, once you show that this is working, how do you calculate moment of inertia about the pivot? That's a parallel axis theorem. So let me write it here. Remind you that I about the pivot, generally speaking, is ICM plus MD squared. This is called the parallel axis theorem. So if we're giving you I moment of inertia about center of mass, and the thing is not oscillating about center of mass, it's oscillating about another pivot point, then you need to add MD squared. What's D? D is the distance between center of mass and the new pivot. So this D right here is distance from CM to pivot. That's the parallel axis theorem. Just to keep that in mind. If you're doing any kind of any kind of torque, angular momentum, any usage of moment of inertia, just make sure that you are using the correct moment of inertia. We will give you ICM. We'll give you about center of mass. But if the rotation is happening about different pivot point, remember to use the parallel axis theorem, add MD squared. D being the distance between center of mass and the new pivot. Okay? But anyway, that's the strategy dynamics. This is the dynamic strategy for oscillator for harmonic motion. Yeah, minus Kx is fine. Yeah, you can use minus Kx. But you need to like simplify your whole analysis to show that it exactly simplifies into minus some constant times x, or minus some constant times theta if you're doing a pendulum. Okay. So that's it. Harmonic motion is like this. Dynamics problem, if you're doing like linear oscillation, F equals MA. If you're doing angular oscillation, it's torque equals I alpha. And then show, like, simplify, and show that it's just minus a constant times the position of the angle. Once you write this differential equation, this is the harmonic oscillator differential equation. We know it. We identify it. So once you write it down, you say, oh, okay, it's a harmonic oscillator. The frequency, angular frequency of this oscillation is just the square root of the constant. Like this C is just omega squared. Like the form of a differential equation of a harmonic oscillator, this C is really omega, what you call omega naught squared. The angular frequency of the oscillation, which from that you can find the period. The period is 2 pi over omega naught, right? So once you write down this oscillation, you can say, oh, okay, so omega naught is the square root of the constant. The period is 2 pi. Let me write the period as well, just so you remember. The period, generally speaking, is 2 pi over omega naught. And omega naught, you can just read it from the constant. It is the square root of whatever constant you found. And then you can write, okay, and the solutions, we don't need to integrate. We never integrate a harmonic oscillator differential equation. We just say, oh, we know this harmonic, we know this differential equation, we know the solution of it. Solutions of it are sine and cosines, like this form. Right? Some constant cosine omega t plus some constant sine omega naught t. Whether it's like a position or angle, it's the same. And then you need to find A and B using the initial conditions given in the problem at t equal to 0. That's the typical harmonic oscillator. First, do the dynamics, either forces or torques. Show that the second time derivative of angular position is minus C times angular position. Then from that say, okay, omega naught is square root of C, solution is A sine plus B cosine, figure out A and B from the initial condition. Okay. So it's a very systematic thing. Harmonic oscillator, just use the correct dynamics equation. If you're doing angle, torque. If you're doing linear oscillation, is force. And find the acceleration in both cases, A or alpha, as a second derivative. So let's do that in our example right here. And again, the solution on MITx doesn't use dynamics, but I want you to use dynamics. I want you to systematically think about harmonic motion as I'm finding the acceleration. That's what I'm finding. I'm either finding A or alpha. That's what I'm doing. So I'm doing F equals MA. So if you write down F equals MA here in this problem, in I hat direction, let's do it. So we did the free body diagram. We had to do it because of dynamics. So we have the static friction force pointing positive. Okay, another thing, static friction force is not equal to mu times n. Okay, so rolling rod slipping gives you static friction always, right? Rolling rod slipping means static friction. This static friction is an unknown force. It adapts to the situation. It doesn't have a particular magnitude. Can take any value from 0 up to mu times n. So if the question doesn't mention anything specific about maximizing it or something like that, it's not mu n. Kinetic friction is mu k times n, always. Kinetic friction is mu k n. Static friction is not. It's just an unknown, we don't know it. It depends on the situation. So you leave it as just Fs. Okay, so writing down F equals ma because we want the acceleration, oops. Okay, so in the positive I hat, we have static friction, and in the negative I hat, we have the spring force, which is minus kx equals ma. That's your F equals ma equation. Okay, that's it. Any questions? Positive static friction is positive, spring force is negative. So this does not look yet like the harmonic oscillator problem. Good question. So, by nature, the acceleration of a harmonic oscillator needs to be negative, right? We want to show that. We want to show it's like minus Cx, right? So that's why in harmonic motion, that's the only place where I want you to keep the acceleration as negative. Like, don't worry about it. We want it to be proven to be negative Cx. So that will come naturally like this. Just leave it as MA. Solve. You will find that A is negative. So yeah, it should be negative. Like the negative should come on its own. That makes sense. We're not talking about the magnitude of A. I'm not trying to solve for the magnitude of A. I'm trying to solve for A, like the component being negative. So leave it as MA. I know that you know it's negative. Eventually it is negative, but leave the algebra lets you, because you're proving, that's the proof you're doing, that A is minus a constant times X. So don't like take that minus away. You want it. I don't know if that makes sense. So in simple harmonic motion, leave like some forces MA, like that's it. So this form of the equation right here looks very similar to our harmonic oscillator equation, except we have this Fs. Like it's not yet ready for like the form. It's not in the form that we're expecting. That's why in this problem, you also have to think about the torques so that you can get static friction. Because I told you before, static friction in rolling rod slipping is all about the torque. It is there to create the torque, right? So that's why I'm gonna do the torque equation as well to try to figure out what static friction is, because I don't know it and I wanna get rid of it. The torque equation looks like this, the torque. As we said, the only torque we have is the torque from static friction, about center of mass. So the torque from static friction is Fs times R, because the perpendicular distance to center of mass is R. The K is a spring constant. The spring force is always minus Kx. That's the spring force. As K is the spring constant. Okay. So the torque equation is torque equals I alpha. So that's I alpha. And I think in this problem, we were given that ICM, yeah, we're given that ICM is 1/2 mR squared. So I'm gonna write it as 1/2 mR squared. And this is about center of mass, so I'm fine. I don't have to worry about the parallel axis theorem. Okay. Yeah, sorry. If S, I mean static, and yeah, if spring is minus kx. So what is missing from this equation is the sign of torque. I need to make sure that this torque, I put the sign for it correct. Is the torque coming from this static friction here? Positive or negative? With k hat, like the question defined k hat into the page, right? So is this torque here into the page or out of the page? Yeah, it's negative. Because as you can see, like look at the picture, we found alpha, like we know alpha and the torque is like going counterclockwise, right? So that's why this torque from friction Fs times R is negative here, because like counterclockwise. Which kind of makes sense. Both A and alpha need to be negative in harmonic motion because it's a restoring force. So both of them need to be negative. So that's basically, look at here, these are the two. This is the force equation, this is the torque equation. Torque is minus, so torque is what? Torque is force times perpendicular distance. The force here is F static. The perpendicular distance to center of mass is the radius. And then this is creating a counterclockwise torque, which here is negative because K hat is defined into the page. When I say K hat into the page, I'm saying clockwise is defined to be positive because clockwise is into the page. This torque is counterclockwise. So now let me simplify here. Well, this alpha is nothing. This is rolling dot slipping. So here is our knowledge about alpha. It is just A over R. This right here is ICM. And this right here is alpha. And this right here is some torque center of mass. This is just torque equals I. Why I did that? Because I wanted an expression for static friction. I wanted to eliminate static friction. And I know static friction is all about torque. So now let's simplify this. You find from this equation right here, you can write it as the static friction force is basically minus 1/2 MA. Eric, the reason here, like the question defined K hat and I hat, but the main reason here is I wanted both of them to be negative or both of them to be positive. But in harmonic motion, as I said, we kind of want the algebra to show that A is negative and alpha is negative, right? So just like the choice here, make sure both of them are negative. Like we chose I hat to the right and A is to the left, so it's negative. We chose K hat clockwise and alpha is counterclockwise. So both are negative quantities, which makes sense in the context of harmonic motion. Both accelerations need to be restoring. So that's why they show that. For torque, you said, okay. Whenever you're doing rolling dot slipping, yeah, you do torque about center of mass. Like sigma torque equals I alpha, you can apply it about different points. But like in rolling dot slipping kind of problem, we do it about center of mass. If you have a problem with an actual pivot, you do it about the pivot. Like if this was pivoted somewhere like here, calculate torque about that pivot. If not, calculate it about center of mass. That's like kind of a good way to think of it. Where did the negative come from? Why is the torque negative again? Okay, isn't R cross F into the page? Let's see. R is pointing downward. 1/2. Okay. I will show you the cross product. Like, let me just answer the 1/2. The moment of inertia of the problem is given to be 1/2 mr squared. So the equation is sigma torque is I alpha. So the I itself, the center of mass moment of inertia, is 1/2 mr squared. That's given. Okay, so that's the one. The negative. Let's do the negative with the cross. I know like many of you do the cross product. So let's see what is happening with the cross first. So we said I hat is like this, K hat is into the page, J hat is down. Do you agree on this coordinate system or no? That's like the trick with doing the cross product. You have to be very careful about things like that. The J hat is down here, not up, because I cross J has to be K. If K is inverted to be into the page, J hat has to be inverted to be down as well. So now R cross F is what? Like this is center of mass, that's the vector R. and this is a vector F. So the torque is R cross F. If you want to do it with a cross, then this R right here is the vector radius vector pointing down, which is J hat. Because J hat is down in this coordinate system. And the force F is positive I hat. So you're doing J cross I, which is minus K. That's where the minus comes from. It's on the cross. If you want to do it with the cross. So that should answer the question about the minus. Without the cross, the way I think about it without doing crosses is just I think about the sense of rotation that this force is trying to make about the center of mass. So what I am saying is just look at the picture here. As the force of friction is pulling to the right, it's kind of trying to make it rotate this way. I don't know, can you see this? About center of mass is trying to make it rotate in this orientation. And that is counterclockwise, so it's out of the page. So that's another way of seeing that the torque from this force is out of the page. Why? Because the sense of rotation is trying to create is out of the page, counterclockwise. Okay, so there's a question about why don't we negate alpha and why don't we negate A as well? That's like the same kind of question. Another student asked before. Again, basically we are trying to show again the big picture for harmonic motion is that we're trying to prove that the accelerations are negative. That's what we're trying to prove. The linear acceleration is minus Cx, where the angular acceleration is minus C theta. We're trying to show it's negative. So if you put a negative yourself, then you kind of like negated that negative that you're trying to prove later. If you put a negative yourself, you're solving for the magnitude of A. You make A positive, but it shouldn't be positive. You wanna make it go to become negative. Yeah, we only would do that for harmonic motion. So naturally, the equation should naturally get you that oh, the acceleration is negative, and alpha is negative, because that's harmonic motion. You need a restoring acceleration. You need it to come back. That's the negative. So you leave the negative to come naturally, which is like here I'm saying this second equation of torque is minus, gives you that the static friction is minus 1/2 MA. Substitute that back into the first equation, you get minus 1/2 MA minus KX is MA. Take the minus 1/2 to the other side, you get basically 3/2 MA is minus KX. Right? And again, our target is to write down the differential equation, which looks like this. So the second time derivative of x, which is the acceleration, is minus k over 3 to mx. That is what we wanted to see. Like we eliminated the static friction force, and we showed that the acceleration, which is the second time derivative of x, is just minus a constant times x. That's it. Like that's really what we want in a harmonic oscillator. So we say, okay, this constant right here, you know what? That's omega naught squared. So we say, well, this is a harmonic oscillator, and the omega naught of it is root 2k over 3n. The period of it is like 2 pi over that. So, but the main physics work here is to write down F equals ma if you're oscillating linearly, torque equals I alpha if you're oscillating angularly. And then from that, naturally, like solve and simplify, you should get to the second derivative being minus a constant times the position or minus a constant times the angle. And that's how you know it's a harmonic oscillator. Any questions? So another harmonic oscillator like the one that you did in the P set looked like what? Looked like this. Theta naught, phi, pendulum is here. The free body diagram here looked like mg and ma. It's like P set 13. Yeah, I will send you the notes. Stop calling me random scammers. Okay. Just like to contrast this with this kind of oscillation, in an angle. Just like remind you, we had the force of gravity and we had this fictitious force. I don't know if we're coming to fictitious force at some point, Coriolis force. But like that's just from PSAT 13, it's very similar idea, except you're doing the oscillation in angle. So since this is an oscillation in angle, like the angle phi here, then you should write down torque equals I alpha. That's your approach. Simple harmonic motion means dynamics. If it's linear, you write F equals MA. If it's an angular thing, you write torque equals I alpha, and hope that this works. That's our show that this works. And that problem, if you remember, this was the pivot point right here. So you had to calculate the torques about this pivot point. So it looked something like this. This length is L. So let's calculate the torques. Okay, let's pick some K hat here. So I'm gonna pick K hat to be out of the page. Into the page. Yeah, into the, I'm gonna choose into the page. So just like quickly show you the approach, like remind you of the approach. So if you do it with MG and MA, okay, why did I pick hat into the page here? I was trying to get away with my choice, but basically, you see how the angle phi is defined, the angle theta is defined from the axis in a clockwise sense. So that's why I chose the clockwise to be my positive. I want to make my angle positive. You could have chosen the other way, but that's why I chose into the page. Because the angle is defined in a clockwise orientation. So that's into the page. So if you calculate the torques quickly, just about the pivot point equals I pivot point times alpha, that's your approach to prove that this is harmonic oscillator and find the constant C and omega naught, etc. So you say, okay, there are two torques here, one from MG and one from MA. Well, the torque from MG about the pivot point now is the kind of idea I'm telling you about. You can think about which way the force wants to rotate the object, clockwise or counterclockwise. If you look at MG right here, MG is pulling down, so it's kind of MG is trying to create this sense of rotation. That's what MG is trying to do. It's trying to push it back, like rotate it this way. And that's counterclockwise, so that's negative in my coordinate system. So one of the torques here would have been minus mg times the perpendicular distance to mg. What's the perpendicular distance to mg? This guy right here. That's perpendicular to mg. That's r to mg, which is just like L sine theta, sine the whole thing. Please correct me if I make a mistake. That's the torque from gravity. Minus because it is counterclockwise torque. Is this correct? And then the torque from the fictitious force is going the other way. It's like trying to rotate it like this, because it's like pulling that. So that's the clockwise torque, which is positive MA cosine L cosine theta naught plus phi, because that's the perpendicular distance is like this. That's equal to the moment of inertia, and you need to correct that with the parallel axis theorem. So it's like ICM. Oh, no, sorry. That's just the point mass. This was a point mass, so just like ML squared. This is the moment of inertia of a point mass times alpha. So that's your main like physics equation. This is clockwise. And then if you follow this approach, like look at how I define K hat in this column. I defined it into the page. So I'm defining clockwise here to be positive, which I can do. Okay. So then like there's lots of like, if you follow this approach instead of the effective gravity thing, if you follow this, like you would have to simplify and like expand the cosine and the sine with strict identities. Eventually you will find that alpha, which is like the second time derivative of phi, with some constant times 3. That's the final thing. So like it's not about the algebra, it's about writing down the correct equation. If you're doing oscillation and angle, you write torque equals I alpha. If you're doing oscillation in linear, you do F equals MA. Will the final give us equation moment of inertia? We will give you the moment of inertia about center of mass. Always. But then you'll need to think about whether you want to correct it with parallel axis theorem or not. But we will give you the moment of inertia about center of mass. The mg L sine theta is because the torque is what it is, the force times the perpendicular distance. That's what torque is. Perpendicular to what? To the force. If you look at gravity, this right here is the full distance from gravity to the pivot. I don't care about the full distance. I only keep the perpendicular part of it. What's perpendicular to mg here? That's what perpendicular to mg. This. That's perpendicular to mg. That's the perpendicular distance to the pivot, and this length is just L sine from the triangle here, because L is the hypotenuse. For the other force, the perpendicular distance is the vertical one, which is the cosine. Okay, so that's a simple harmonic motion. Very kind of systematic. Just think linear or angular. Linear F equals MA, and then simplify it to find the differential equation of the form you like. Angular, write torque equals I alpha and simplify until you get the differential equation form that you like. And then once you find that form, you say, okay, it's a harmonic oscillator. The solution is sine and cosine. The omega naught is the square root of whatever constant you found, just like here. This differential equation means this is omega naught, and also mean that the solution, if you ask you what is the solution, what's x as a function of t, you say, okay, it's a cosine omega naught t plus b sine omega naught t, and find a and b from the initial conditions. Yeah, any trig identity. Don't worry about like I don't think you're gonna have to worry about trig identities. Like we're not like asking you like weird, long, messy calculations in the exam. So, but yeah, if something like that will give you. The period is 2 pi over omega naught. So once you identify what's omega naught, 2 pi over that is the period. And omega naught is the square root of whatever constant you found, without the minus. Without the minus. Like this is the constant here, without the minus. That's omega naught squared. And then the period is 2 pi over omega. That's harmonic motion. Okay, so the general slide again is here. Be careful whether you're doing angular or linear, and then from that write either forces or torques, and then from that show that the A or alpha follows the differential equation of a harmonic oscillator. Any questions about harmonic motion? Okay, so we talked about rotation and translation, rolling without slipping, static friction, and rolling without slipping, making the necessary torque for alpha to match ACM. And we have been like dealing with, okay, how to approach this, how to approach that using either dynamics or energy, conservation general. So we did stuff with dynamics, like the pulleys, like the harmonic motion has to do dynamics because it's the acceleration that matters. Circular motion is dynamics. And we did a problem with conservation when we thought, okay, what is conserved? We didn't have to do dynamics there. So let's see what we did so far. We talked about general problem solving strategy. We've been applying it. We did rotation and translation with rolling dot slipping and static friction. We did harmonic motion. So now we want to talk about collisions in a rigid body sense, orbits, and Coriolis. So we have like about 1 hour to cover these. So let's get to it. So another kind of rotational thing is like, okay, what happens if you have a collision between a rigid body and like a point mass? We've seen like variants of these over the course of the semester. And this is like a good application for the final exam. Do I have? I didn't put this one. Okay, I'm gonna try to remember it. Okay, so there was a problem in week 15, day 1 practice. I just want to like look at it quickly. It had a rod and this rod was pivoted from here, just like fixed from this point, and you hit it with a ball MV0, and this is like M rods. And we're asking basically the following question, the length is L. We're asking the following question, we're asking what is the minimum value for V0, such that this rod will, after the collision, so it collides and comes forward with V0 over 2. Like after the collision, it moves with V0 over 2. The other way, like same way. And the rod now is gonna go up, all the way up after the collision to the horizontal position. So we want to find V0 that will allow us to do that. So first of all, this is a two-stage problem. So you need to also think about whether you have many stages going on in the problem. And that's usually when you have a collision. When there is a collision in a problem, so this is a rigid body colliding with a point mass. That's like the topic we're discussing, the family of problems. So we want to find V0 such that rod makes it up. So since we have a collision going on, the general case, as I said in the previous review session, is you need to stop, basically you need to stop and treat the collision itself as its own stage. And then worry about what happens later, worry about what happens before separately. Here, this problem, you can split it into two stages. Just two. Because the first interesting thing that happened is a collision. The problem starts immediately. The first thing happening is a collision. That's something that you need to stop and deal with separately. Please remember this. If you have a collision in any problem, stop and do it separately. And then, like next, like the rod is gonna go up. That's its own separate stage. Okay. So for each of these stages, we need to think what approach we're doing. Dynamics or conservation. So basically, dynamics is if you have harmonic motion, if you want the acceleration, if you want time, none of these exist. Like we don't care about the acceleration of the rod. We don't care about the time it takes to go up. We don't care about the force. All what we want is the initial velocity. So we're not doing dynamics. So since we, like the question is saying just find V0, we're not interested in any kind of dynamical quantities like A and time and force, then we're just using conservation. All through this problem, it's just about something is conserved. Okay. So during the collision, we go and ask ourselves, okay, let's see, something is conserved. Is energy conserved? Is linear momentum conserved? Is angular momentum about some point conserved? So that's the typical thing. So that's like the main topic here. There is a collision between a rigid body, like a rod. It doesn't have to be a rod, like any kind of rigid body, like a wheel. You can hit a wheel. Okay? You're colliding with a point mass with a rigid body. And this collision, you want to treat it with some kind of conservation. So we have to be very careful here, because collisions have their own particular like kind of ideas. The first idea is energy. Energy in a collision is not conserved unless the question says elastic. And we said that previously, and we say it again. Every collision in the world is inelastic. So unless we tell you, assume this is perfectly elastic, only then energy is conserved. So that's like, so energy is not conserved, generally speaking, in two situations. If you have kinetic friction, that creates non-conservative work, like the problem with kinetic friction in the wheel. Energy was not conserved because kinetic friction is dissipating energy. And the second thing, if you have collision, inelastic collision, and every collision is inelastic, unless we tell you it's elastic. So since the question here, so you ask yourself, did the question mention, it has to mention this word, this is a magic word. The question has to tell you this is elastic. This particular question did not mention it's elastic, so we cannot say energy is conserved during the collision. So please remember this. When you have a rigid body colliding with a mass, look for the word elastic. If it doesn't exist, then energy is not conserved during the collision. It's inelastic. Inelastic means energy is lost. Because when you're colliding with something, you lose energy to heat and sound and deformation between the objects. Like that natural thing is that you're going to lose energy from the collision. So that's realistic case. Unless you say, okay, it's perfectly elastic, then we're just like ignoring all of that. So you have to look for the word elastic. Other than that, energy during the collision is not conserved. Okay, so when I did this problem in class, like many students just immediately thought energy is conserved in the collision. Don't know like why, but no. Collision, think elastic or inelastic. Doesn't say anything, then it is inelastic. So you cannot say energy is conserved. Is this clear? Any questions? Okay, what about linear momentum? Well, we said that the condition for linear momentum is that there are no external forces. So let's look at this example right here. So again, you might be tempted to say, okay, yeah, there are no external forces, like momentum is conserved. However, in these kinds of collisions, if there is a pivot, that's like the second important idea here. So first important idea, elastic or inelastic, that's for energy. Second important idea is a pivot. Pivot or no pivot? Do you have a pivot in the problem? Is your rigid body pivoted somewhere? If it is pivoted, momentum is not conserved. If there is no pivot, then yes, momentum is fine. Because the existence of a pivot immediately introduces pivot forces. Like the pivot is holding the object somewhere. And as you hit it, the pivot is going to react with some forces. So the pivot is going to apply some kind of like pivot force in the X, pivot force in the Y. So there are forces at the pivots. The pivot acts with pivot forces. So that's why no, because of pivots. So pivot forces, let's say, so that you can see it easily here, there are pivot forces. So momentum is not it. So these kinds of problems, when you have a collision with a rigid body, ask yourself this question: do I have a pivot or no? If I do, momentum is not conserved. If I don't, momentum is conserved. Is it elastic or inelastic? If it says elastic, energy is conserved. If it doesn't say elastic, energy is not conserved. You had a problem in the P set. I don't remember which P set, but you had a problem like this where all three were conserved. Do you remember this problem? Like you wrote down the three things conserved in a collision like that? Like you wrote energy and you wrote momentum and you wrote angular momentum. Why was that the case there? Because the question said elastic. Go back and find this piece of where you wrote collision like that and you wrote down the three conservations. The three conservations were fine. Why were they fine? Because there was no pivot. The rod was not pivoted there. So momentum was fine because there are no external forces. Here we have a pivot, there are external forces. So momentum is not. In the P-set problem where everything was conserved, it said elastic. The question specifically said this is elastic. That's why you also said energy is conserved. Here it doesn't say elastic, so it's not conserved. So be careful, okay? Elastic or no elastic? Or inelastic? Pivot or no pivot? Pivot means, pivot forces means momentum is violated, okay? So again, we come back to our last resort here, which is angular momentum, which is, okay, can we find the point where angular momentum is conserved? Well, yes, the forces that created the pivot forces that violated conservation of momentum, if we pick the pivot itself as a point, then they don't create torque right there. Like this point right here, the torque about this point is zero because these forces act right there. So that's why when you have a pivot, you can choose this pivot point. Angular momentum of the pivot will be conserved. Because torque about the pivot is zero. That's what happens when you have a pivot. When you have a pivot in your collision, angular momentum about the pivot is conserved because whatever forces exist at the pivot will not create torque right here. And if there is no torque about the point, angular momentum about the point is conserved. So that's our analysis of the three conservations in a collision with a rigid body. Energy, elastic, inelastic, that's the determination. Momentum, pivot or no pivot. Pivot, then no. No pivot, then yes. Momentum is fine. Then angular momentum is always going to be conserved. If you have a pivot, it's conserved about the pivot only. It's not conserved about any other point, by the way, here. Angular momentum, you cannot find any other point. Because if you pick any other point, the pivot forces will create torque there. It's only the pivot where the pivot forces don't create torque. So angular momentum about the pivot is conserved, but angular momentum about any other point here is not conserved. You see that? So that's why the solution for the first stage is just conservation of angular momentum before and after the collision about the pivot. So as we said, angular momentum has two forms. If something is just translating, that's MVR, perpendicular, and if something is spinning, it's I omega. So initially, we did not have any spinning, any rotation. It was just this point mass moving. So it had MVR, that's the angular momentum initially. R perpendicular to the pivot is L, because the point is at an L from the pivot. And then after, we still have this kind of angular momentum, but with V naught over 2, because it goes like with V naught over 2, goes forward. And then now the rod is going to start spinning, a rigid body spinning, so that's I about the pivot times omega. That's stage 1. That's the equation for stage 1. Conservation of angular momentum about the pivot. Don't forget that it's about the pivot, so the moment of inertia should be about the pivot, not about center of mass. So you need to use, if you look at the solutions for this problem, we use the parallel axis theorem because we're not spinning, the rod's not spinning about center of mass, it is spinning about the pivot point. Yes, and something is translating, like this guy right here, that's translating the point mass. So that's why we have the MVRs, MV L over 2 and MV. Because initially it was translating with V naught at distance L, finally it's translating with V naught over 2 times distance. So that's the two types of angular momentum that exist. Translation is MVR, spinning is I omega. So any question about the stage of the collision, like this idea of elastic, inelastic, pivot or no pivot for the usual, the three different conservations? Okay. The second stage is just, okay, the collision is done. And now the rod is gonna start moving with some omega. That's the omega that you found from the first stage. And it's gonna go up until it's like completely horizontal like this. And when it goes up, omega goes to 0 because we want to stop. We want to see what is the minimum like coming velocity, so we can just barely makes it. Barely makes it, so it's gonna stop at the top here. So that's a conservation of energy problem. Why? The pivot forces still exist, by the way, so they violate conservation of momentum. The reason that why we choose energy here is going up and down. Just keep that in your problem-solving toolbox. Anything that goes up and down, energy is the best way to do it because energy deals with MGH, the heights. So anything going up, going down, that's conservation of energy. So the second stage here is conservation of energy. And as I said, remember that energy in rotation is 1/2 I omega squared, and energy in translation is 1/2 mv squared, the kinetic energy. So the equation here very simply is the initial energy is equal to the final energy. So the initial energy has 1/2 I about the pivot omega squared with this guy, again, this omega from the first stage. That's the kinetic energy at the beginning. And then I need to figure out the potential energy of the rod. Potential energy is mgh, so I need some reference for the y. That's all what you do for potential energy. You need to define where is y equal to 0 so you can see the heights. Because there are no non-conservative, energy is conserved because there are no non-conservative forces, meaning that there are no friction, basically, no kinetic friction. So that's the, like during the collision, you lose something because of the collision. That's like the nature of collisions. But here there is no collision, no friction, so energy is conserved. So you don't have, if you don't have any elastic collision and you don't have kinetic friction, then energy is good. And if you're going up or down, that's usually energy and energy stage. So I'm gonna set the y equal to 0 at the top here. I'm gonna say this is my reference for y equal to 0. You can set it anywhere. Just for the MGH, I need some reference. Okay, so another important fact here is when you do MGH for a rigid body, the rigid body is like this. Every point in the rigid body has a different height. So it can be tricky, like figuring out MGH for the whole thing, because which height do I pick? So the height you pick for the rigid body always is the height of the center of mass, because the center of mass is the effective point where gravity is acting. Gravity is right here. And it's all about MGH. So it's always the height of center of mass that matters. This is where gravity is acting. So gravity is acting at this height. A common mistake is to pick the total height of the rod as if this is the total MGH. No, it's all about just the center of mass. The center of mass is the effective place for gravity. So that's why initially center of mass was here at like this L/2. And finally, center of mass is here at 0. It's all about the height of center of mass in MGH. So the initial height of this rigid body with this reference is minus L/2. Why minus? Because it's below my reference. That's the initial potential energy. That's kinetic from rotation, and that's potential. Why negative? Because I chose the height at the top to be 0, and this is below the 0 with L/2. Now the final energy in the final situation here, it's gonna stop rotating, so it's 0 kinetic, doesn't have any kinetic at the top, and the center of mass is exactly at the reference, to no potential as well. This is equal to 0. Total energy at the end is equal to 0. That's the second stage. And now just combining the two stages here, that's it. So you see with conservation of stuff is kind of easier because you write down one line, like the solution for each stage is just one line. Momentum is momentum. Energy is energy. And just like a final remark in this, look at the full solution, but the moment of inertia about the pivot is the moment of inertia about center of mass plus md squared. This is the parallel axis theorem. We needed to do that here because the rotation of the rod is happening about the pivot, which is not the center of mass. So if we give you ICM, you need to add the md squares from the parallel axis theorem, where d here again is the distance between the pivot and center of mass. So it's L/2. So like here, this is m L/2 all squared. That's I about the pivot that you're using in both these equations. So that's again an application of our general problem solving strategy. We didn't need to do dynamics because we don't care about acceleration or time. And it's not a harmonic motion or circular motion. And then, so we're deciding what conservation we use. During the collision, there was a pivot, so momentum is no. It was inelastic, so energy is no. So it's only angular momentum about the pivot, so that there are no torques about this point. That's conserved during the collision. So we wrote down angular momentum before, angular momentum after are equal, and angular momentum can have a translational term MVR and can have a rotational term I omega. Initially, we just had an MVR from the ball. Finally, we have MVR of the ball and I omega of the rod. Then after the collision, now the rod is going to start with this omega and end at 0 energy here. So the energy at the beginning is energy at the end, and we wrote down the energy. Yeah, the potential energy initial is negative. This is K initial, and this is U initial, and this right here is the total energy final. So I define the reference of Y equal to 0 at the top. The rod is below the reference, so the height of it is negative L/2. If it was above the reference with L/2, it would be positive MGH, but it is below the reference. I could have chosen the reference down here, then everything would have been positive, but you can choose the reference anyway. Okay, there is a question why we're doing 2 stages instead of 3 stages. Well, that's a general, like generally speaking, there should be as many as 3 stages, but some problems will just go straight to the collision. The 3 stages that I talked about in the previous can still happen in the previous review session. If you had something interesting going on, like some physics, some event going on before the collision, then you have to stop and do it. But it just happened here in this problem that the first interesting thing is just a collision. The first thing happening in the problem is the collision. For example, let's say if this question was the same, but instead of starting immediately with the collision, this ball started from a slope and it went down the slope and then it hit the rod. And that would have been a stage before that you had to do. But just like it just happened in this problem, the first interesting event is the collision. So we just had the collision, then the interesting event of going up. That's another interesting stage. But yeah, generally speaking, you can still have 3 stages. Yeah. So just think, is there something interesting before the collision started? And is there something interesting, some event after the collision ended? Sometimes you don't have like, so sometimes you have the 3 stages, sometimes you have 2. Sometimes it's just all about the collision. The question can just give you the collision, that's it, and just 1 stage. Okay? You just have to read the problem and figure out how many different events, how many different stages are happening. Is omega acting center of mass, that's why radical rotation varies from the pivot to center of mass of the rod. For the private question, are you talking about the height, the L over 2 in the height here, or are you talking about the L over 2 in the parallel axis theorem? Okay, so for the height, it's because gravity acts at the center of mass, not omega. Like omega is the rotation about it, like omega is like it. It's because gravity, mg, acts from center of mass. So the gravitational potential only cares about where gravity acts. So that's why mgh, from now on, whenever you're writing mgh, you're writing h of center of mass, because that's where gravity is. Okay, so I want to actually go back at the very beginning and add this to your energy calculation. Here, I wrote down the general form of energy is 1/2 mv squared if you're translating, 1/2 I omega squared if you're rotating. And U, I'm going to write this U as, so you see it here as mg, height of center of mass. That's how you write mgh from now, because that's where gravity acts. Okay. All right, so that takes care of the collisions. So just think in collisions with a rigid body, is it elastic or inelastic? Is there a pivot or no pivot? Usually angular momentum will be, you use angular momentum, but the question is about, am I also using energy? If it's elastic, yes. Am I also using linear momentum conservation? If there is no pivot, yes. But if there is a pivot, you eliminate momentum. You don't use momentum conservation. And if it doesn't say elastic, you don't use energy. That's the strategy here. All right, so the last 2 things. Why do we use I of the pivot on the energy equation? I is about the point that you're rotating about. The moment of inertia in any context is about the point that you're rotating about. So in this problem, the rod was pivoted from right here. So when you hit it, it's gonna rotate about the pivot here. So that's why we use I about the pivot, because the rotation is happening about the pivot, not about center of mass. Rotation about center of mass looks like this. That's rotation about center of mass. That's not what's happening. It's happening like this, about the pivot. Yeah. Okay, so the last 2 things I want to talk about are orbits and Coriolis. So again, just so you don't lose focus, kind of all what we've been talking about, except for harmonic motion, is rotation and translation. So we've been dealing with objects that rotate and translate. So we did the pulleys. The pulleys rotate, the blocks attached them translate. We did that. We did like something that both rotate and translate at the same time, like the rolling without slipping. We said how to find static friction, how to calculate torque. Do we use dynamics or do we use conservation? And I want you to apply these ideas, like look at the problems again and like approach, okay, dynamics, no, conservation. What conservation? Like apply this to other problems. There are external torques. Okay, the question is why there are no torque about the pivot, because the forces of the pivot on the rod exist right here at the pivot. So they don't have a distance from the pivot. Torque is force times distance, perpendicular distance. So if they act right here, they create no torque here. That's why this pivot point, there is no torque about it, because the pivot forces don't have a radius from this point. Okay. So we did the rotating and translating objects. We did the collision with rotating and translating objects. So we do conservation of the suitable thing. And we talked about harmonic motion, which is just you do the dynamics, either linear dynamics, force equals ma, or angular dynamics for oscillations in a pendulum, torque equals I alpha. And from that show, it follows the harmonic oscillator equation. So now it's time to look at two other cases. The final is focusing on what I'm focusing on right here. It's like that's the focus here. Caroline, about what point? That's an important question because torque is about points. Force of gravity does create torques about other points, but never creates torque about center of mass. Yes, because it always acts from center of mass. So it never ever creates torque about center of mass. Gravity never creates torque about center of mass. Yes, but it creates torques about other points. Okay. Okay, so let's look at orbits, which is like a very systematic topic. Like you see like a problem with orbits, circular orbit around the planet or a sun, a star, or an elliptical orbit. A very systematic thing that you do. So let's do that and then talk a little bit about Coriolis, and that's it. And again, I thought about this review session for a really long time. You can say years because I take the year before and I adjust it. And I really think that if you follow this and you practice on it, you'll be fine for the exam. Okay, like a review session with all the detailed topics, the specific topics we discussed, and the detailed like problem solving ideas. I think you'll be fine if you follow them and do them on your own. Like practice on them on your own. Make sure you understand everything that we talked about today. So for the orbits, we are talking about something that is orbiting around something else. Okay, so two masses. We have two masses. I'm calling them here big M and little m. And we are going to always work in this limit. The big mass at the center is much heavier than the small mass around. This limit makes it much easier for us because if you remember, we did the Kepler problem in class. We talked about the reduced mass of the system. We talked about, it was a complicated kind of analysis because if the two masses that are orbiting around each other are comparable in mass, both of them are going to spin. But if you assume that the mass at the center is much heavier, like the sun is much heavier than the Earth. So basically you can ignore the motion of the sun. And that's the limit we're gonna always work in, the simple limit that the central mass M is fixed. That's basically what we're dealing with here. The big mass is fixed, the small mass orbits around it. Okay. So we have two types of orbits that come in this course. Circular. So you're going in a circle around so this is how it looks like. So there's a big mass M. That's fixed, not moving. We don't have to worry about it. And there's a little mass M orbiting with a radius in a circle. And then the second type of orbits is the elliptical orbits. And that's like the more like realistic orbit, like most orbits are elliptical. But the elliptical orbit looks like this. So the big mass exists somewhere here, and the little mass is orbiting. And we are going to focus on the ellipse. The ellipse is a complicated shape, much more complex than the circle, of course. But our focus is going to always be about the 2 points in particular that I'm showing here. When the orbit, when the mass is at the nearest approach, the closest to the sun, and the furthest approach. So the picture in the circle is that the radius is constant. You're moving in a circle, so your radius is constant. That also means that your velocity your speed is constant. If you're moving in a circular orbit, you're moving with a constant speed. The usual thing we want from orbits actually is to find the speed. Like the usual thing we want to ask you about. It doesn't have to be like that, but usually we're interested in knowing what is the speed in the orbit. As you're going in a circle, what's your speed? As you're going in the ellipse, what's your speed? In the ellipse, the speed is not constant because you're changing radius. Like for example, this right here is RA, this right here is RP. So you need someone to confirm that the A and P notation that I'm using here is correct. Because I always forget which one is called A and which one's called P, but I feel like this is correct. This is it. The big one is A. Okay, thank you. So they have like these names, like I don't know, they are Greek names or like I don't remember them. But is there basically the furthest approach, the furthest away from the sun you are, and the closest away that you are. At these two particular points, we call the velocity here VA and VP. Okay, so the idea here is that V is not constant in an ellipse because you're continuously changing your radius. You're changing your distance from the sun, from the star, from the big mass M, so you're changing your speed as well. So the main things again that we're interested in is finding the speed. So in the circle, we want to find the speed. Something is moving in a circular orbit, and we want to find something, usually the speed in the orbit. What do? Well, we come back to our problem-solving strategy. Yes, it's like a completely different context here. We have orbits and space and stuff, but still, A21 is all about you're either applying dynamics or you're applying something that's conserved. So circular is circular motion. You have a circle, you're moving in circular motion, and as I said at the beginning, circular motion is all about the centripetal acceleration. If you have something going in a circle and you don't use the centripetal acceleration, then something is wrong because you haven't used the very valuable information about the geometry of the point. Geometry of the circle means you're accelerating with minus v squared over r radian. So that's why circular orbits, there is nothing else than to do dynamics. We use dynamics. Why? Because circular motion is dynamic. We want to utilize the acceleration in a circle. So what's circular motion? Like what's the dynamics here? Well, the main force on our object is the force of gravity. The circle has an r hat. Define the polar coordinates is just always r hat pointing radially outward. So the force of gravity is inward, which makes sense because you need a force creating the inward centripetal acceleration. So the dynamics here is very easily in the r hat direction. The equation is minus gmm over r squared. This is the force. This is the force of gravity. Why minus? Because it's inward, and r hat is outward. So it's against my r hat. And this is the form of the gravitational force, gmm over r squared. So this just supplies the centripetal acceleration, so it's equal to minus mv squared over r. Minus because the acceleration is negative. The centripetal acceleration is inward as well. So this right here is ma radius. So that's it. Like circular orbits, there is really nothing else you do in a circular orbit other than writing down dynamics equation. And you can rearrange this equation and find that the velocity is just like cancel stuff, m with m, r with r, minus with minus, and it becomes root gm over r. So that's the velocity in the circle. That's the exercise you do every time you see a circular orbit. That's the only piece of information you have here. Dynamics, because you want to utilize the acceleration in circles. That's what you do. Circular motion is dynamics. Harmonic motion, dynamics. So that's it. That's all about the circular motion, circular orbit. Any question about dealing with circular orbits? Now we found the speed in the circle, which is constant. It's always moving with this speed. Any question? Okay. The right side is negative because the acceleration, the centripetal acceleration that we know is always inward. It's always pointing radially inward. Like when we did the kinematics of circular motion, we studied the geometry of the circle, we found that it has to be, the object has to be always radially inward, accelerating radially inward. So that's why the acceleration is inward, the force is inward. So both sides are negative. So that's what we do with circular orbits, very straightforward, F equals ma, find the speed, done. The ellipse, as I said, is more complex because you're changing your speed and you're changing your distance. However, we can think about what to use as always. So are we using dynamics? Well, we're just interested in the speed and the distance, and we don't have a particular form. This is not circular motion anymore. Ellipse is not a circle. So we don't choose dynamics. So no dynamics because we don't have to. We don't have any particular acceleration We don't know the acceleration. We don't have any interest in the acceleration. So this is not dynamics. So if you see an ellipse, you don't use dynamics, you use something that is conserved. So you think what is conserved? And you did this many times. You wrote it in the PSET, in a PSET before. You did it in class group problem about what to do in an ellipse. And as we discovered together, there are two quantities that are conserved in an ellipse. Energy, because there are no non-conservative forces, like no friction, nothing. So energy is fine. So you write down energy is constant. And also angular momentum is constant about the central point. Angular momentum about the center. So we did that many times before. And the reason that angular momentum is constant is because there is always no torque about the central point. Because the force that exists is the force of gravity, which is always pointing towards the center. It's always parallel to the radius of the center. So never creates any torque about the center. So from now on, whenever you see an ellipse, an elliptical orbit, there is nothing else to do other than write down the two conservations. Conservation of energy, conservation of angular momentum over the central point, and we're only considering these two special points. Any other point in the ellipse is much more complex, and I don't think you need to worry about that. It's only the nearest approach and the furthest approach. So let's write down together the two conservation laws. You did that in class, and you did it in the PSET. Let's just remember that. So the energy equation is what? Well, there is potential energy minus Gm over R. So I'm going to say RA. So don't forget, it's not the center. I don't mean the center of mass. I mean the center as M. Yeah, like let me know. Like about M. Let me write it like that. Yeah, I mean, because it's not, well, technically speaking, sorry, starting to get very tired, but we can finish this. Coriolis is coming next. Technically speaking, if the mass at the center is much bigger than the mass at outside, then center of mass is technically at M. So it was fine as well. Because it's like much heavier, so center of mass is right there. So yeah, the energy has potential energy minus Gm over R. That is the potential energy of gravitational force. We derived that long time ago. It's given in the exam. Don't forget the minus. Common mistake is to forget this minus. The potential energy itself is minus Gm over R. The force is minus Gm over R squared. So anyway, the energy is minus Gm over R, and then you have plus 1/2 mv squared. This is at point A. That has to be equal to the same thing about point P. That's energy conservation. And then angular momentum about the point, this is just a translational motion. Like if you look at this instant, this is a point mass moving with V, the point mass moving with V, so that's just MVR. So you get this equation, very simple equation, MVA or A is MVP or P. That's angular momentum equation. So that's what you do. Like the orbits problems are very well defined, like you know what to do. Circular motion, if you have a circular orbit, just write F equals MA and find V, just like this part. If you have an ellipse, write down the two conservation laws at the two special points, which is can all look like this. So what is happening here in terms of problem solving? Squared, no, the R squared is a force. So the gravitational force is like 1 over R squared. The gravitational potential is 1 over R. It's like 1 over R. So be careful. Like the left-hand side with the circle, we used forces, so the force has an R squared. The right-hand side, we're using energy for the ellipse. The energy is 1 over R, not 1 over R squared. Minus Gm over R is the potential energy. Okay. So what's happening here? Oh, sorry, no. Even angular momentum is, if you remember, angular momentum has two forms. I omega, if you're spinning, and MVR perpendicular. It's not R squared, MVR. We don't have I omegas here because we're assuming this is just a point mass that's orbiting around, and it's not spinning. If it's spinning about its own center of mass, then it would have had I omega as well. It's not doing that. We're just assuming it's just translating. The I omega, if you're spinning about your center, that's I omega. We don't have it. Okay, so yeah, I omega is one form of angular momentum. We don't have it here. MVR is another form. We have it here. Okay, so what is happening in an ellipse? Usually, this is what's going on in an ellipse. We have two equations, right? Energy and angular momentum. You have to use them in an ellipse. You have to. Okay, so which always look like this. So you have two equations and you have four quantities in an ellipse, as I showed you here. Speed at A and radius at A, speed at P and radius at P. So usually the question will give you two of these four and will ask you about the other two. We have only two equations to write: conservation of energy, conservation of angular momentum. The question will give you two and will ask you to find the other two. So like, for example, knowing RA and VA, you can find RP and PP from the two equations that you have. Knowing the two radii, you can find the two speeds. Knowing the two speeds, you can find the two radii, so on. These are the variations here. But in all cases, we write down the two conservations and solve for the two unknowns. But there's always like these four quantities. The question will give you two and you solve for the other two using the two equations, two unknowns. The algebra here might be a little bit messy, so prepare yourself for working through the algebra of these two equations, because you have quadratic stuff like 1/2 mv squared, etc. So work through practice problems here and make sure you can solve the algebra. But at the end of the day, you're writing down these two equations in an ellipse, and you're using the two things that you know to find the other two that you don't know. Out of the two radii and the two speeds at the 2 points. You're given two, you find two from the two equations. Okay? So that's it, like very, very, very systematic. So just quickly, because I need to have time for Coriolis, this is a practice problem. I don't know, like the number, I think it's called space debris or something like that. So basically you have an object initially going in a circle, and then it collides with some other object. And then after they collide, they start going in an ellipse. This is the problem with stages. Again, the stages usually come when you have a collision. So if you see a collision in a problem, stop and say, okay. How many stages? Do I have something before the collision? Here, yes, I have circular motion. Like I have to worry about the circular orbit. So here, basically, stage one is a circular orbit. This guy was just moving in a circular orbit. What do I do in a circular orbit? I write down dynamics. So it's just minus gm over r squared is minus mv squared over r. And from that, the velocity in the orbit was gm over r, and this was called our a, like the radius is r. So that's the first stage, just circular orbit. That's what we do in a circular. So we found the speed in the circular orbit. Then the second stage, if you read this problem, it collides with this debris thing and sticks to it. And it was moving with VD, the other one. So stage two is just saying, okay, that's the collision. You do the collision separately. And now this is just a simple collision with conservation of like linear momentum. Like we don't have rigid bodies here. We just have 2 point masses colliding. You don't have to worry about anything other than momentum. So you have something like, okay, m satellites times the velocity of satellites, like here, plus m debris plus velocity debris is equal to the total mass after the collision times the final, like that's, we did that before. Right? So just like using this right here, you can find the speed that they meet with after the collision. And then they say, okay, after they collide and stick together, now they move in an ellipse. And they ask you find the ratio between the radii, like something like that. But either way, whatever they ask, we'll treat an ellipse. So we are going to just write down the conservations, like, and then see what we can do. So the conservation is, again, 1/2 mv a squared minus gm m. This is m. Don't forget that this mass is the mass of both of them together after they stick together. This is going to cancel out from the energy. So anyway, this is RA equals 1/2 mvb squared minus gm mrb, and that's energy. And angular momentum is like mvara is mvp or prp. And then you see what we want here. And the platforms always stay okay, the question about, okay, like this particular practice problem kind of splits itself into, okay, part A, stage 1, part 2, find the collision, part C, find, it doesn't have to tell you that. You could ask you the final thing, and you will have to split it on your own. So it's a good practice for you to practice, okay, I see a collision, so I'm gonna split the problem into pieces. The collision itself, I'm gonna do it separately. If there is anything before it, I will do it separately, then the collision, then something happening after. So here I have a circle, then the collision, then the ellipse. So you have to practice on getting the stages yourself. It could like split it for you, but it could also just tell you, deal with it, and then you'll have to split it on your own. Okay, and yeah, so basically, what are the two things? Remember in the ellipse, I told you, basically, you know two things and you're solving for the other two from the two radii and two velocities. Let's see which two do we know here. We know the speeds. You see, we just solved for V final. That is the velocity that if they collide like here, this is gonna be the velocity here. Like, you know the velocity here, the speed at this point after the collision. So you know the speed there in the orbit, and we know that radius as well, because that's just the radius of the circle. I don't know if you can see this, but this guy was moving in a circle, collide with something else here, and now they're gonna start moving in an ellipse. But at this point right here, immediately after the collision, we just solved for the speeds here from the collision. So we know the speed here in the ellipse. And know the radius here is just the radius of the circle, because it was moving in a circle at that point. So in this kind of problem, we know VA and RA, and we can find VP and RP on the other side, basically. You see what I'm saying? You know here, like from the collision, you know V at this point, which is in an ellipse now, and you know the radius at this point is just the radius of the circle. So now we can use the two equations to find, okay, what is the speed on the other side of the ellipse, and what is the radius of the other side of the ellipse, because you have two equations and you can find the two angles. Does that make sense? Any questions? So all in all, circular orbits is centripetal acceleration equal to the gravitational force. Elliptical orbit is conservation of energy and conservation of angular momentum. And then you can solve the algebra. Any questions about orbits? I need to drink, so give me a minute, and then I'll drink something quickly and come back to discuss Coriolis. That's the last thing we want to talk about. Okay, so be right back. All right, so we're almost there. Again, the concepts we discussed today are all very important. And if you just like focus and concentrate and practice on this, practice on orbits, practice on rolling loss slipping, and on collisions with a rigid body, simple harmonic motion, just practice using the ideas we talked about, you will be fine. You will be fine for the final exam, trust me. The final thing you need is the idea of Coriolis. And I'm gonna focus in particular on Coriolis out of the fictitious forces. And in particular, I'm gonna focus on Coriolis at the surface of the Earth. Because we live on Earth, the most important application of this whole fictitious forces thing is how Coriolis affects us on Earth. So Coriolis as a force, like this equation, you will be given that equation. So it's minus 2m omega cross v prime. So if you live on a rotating frame, you exist in that rotating frame, okay? And you start moving in the frame. So the frame itself is rotating. You're rotating with it, okay? But on top of that, you're moving. So it's like you on Earth and you start moving on Earth. Like we walk on Earth. Like while we're walking or running on Earth, that's our v prime. V prime is velocity relative to the Earth, velocity in the frame. And omega is omega of the Earth, the rotating frame. So the main thing that you really need to worry about here is how to calculate the Coriolis force in different scenarios, which is basically how to perform this cross product. Okay, so this is omega cross v. If you know what omega is, we know what v prime is, do the cross. By the way, there's a question, why is there two in here? Well, like, why does it even look like that? That's like a bigger question. Like, I don't believe we showed you the derivation for that because it's like too messy. But there is a tool. Like once you analyze what's going on with all the algebra of moving between frames of reference, it comes out to be like that. So sorry, I cannot like give you a more satisfying answer. But the derivation of this equation is like kind of out of the scope of the course, really. But there is a tool. So I can send you the derivation, and you can see why there's a two, but it's like messy a little bit. So the way that I perform cross products is using these cycles. I believe I talked to you in the previous review session, maybe about the idea of having a positive cycle of crosses. So we have three different coordinate systems now in the course: Cartesian, cylindrical or polar that we use for circles. And now we're dealing with spherical coordinates because we're on Earth and we're treating the Earth as a sphere. So the coordinates go like this. In Cartesian, we have I, j, k, right? And we define the crosses to be I cross j is k. So knowing that I cross j is k, you can complete a cycle here. I, j, k, I. If you go with that cycle, it's a positive cross. If you go against it, it's a negative cross. So for example, I cross j, that's with the cycle, so that's positive k. Like gets you the next with a positive number. But if you go the other way, like if you do I cross k, like this, if you want to do I cross k, that's against the cycle. So you get minus j. Okay, so that's my favorite way of like doing these crosses. Just like write down this positive cycle and see whether you're doing this or you're doing that, then you know it's a positive or negative cross. So the IJK that works for Cartesian, similarly in polar or cylindrical goes R theta k. So R cross theta is k, and you can continue this cycle. So R cross theta hat is k hat. That's the cylindrical part. For Coriolis on the surface of the Earth, we're doing spherical coordinates. Why? Because the Earth is just like kind of a sphere. The spherical coordinates go like R theta phi. So you kind of need to remember that R cross theta, R hat cross theta is phi hat. This is a coordinate system that we're talking about in spherical coordinates, and you need to know all the permutations here. Like what is theta cross phi, what is phi cross R, what is R cross phi. Like, so all these combinations, you can get them from this cycle. Just knowing that R cross theta is phi, you can construct R theta phi R, and then you know what to do. Going this way is positive, going that way is negative. So I want you to remember this. Like R theta phi is the order in spherical coordinates in terms of cross products. So any questions about the positive cycle R theta phi in spherical coordinates in terms of crosses? So remember this R theta phi. All right, so what are these? Like, what is the meaning of these R hat, theta hat, phi hat on the surface of the Earth? That's another very important point. Super important for like the Coriolis calculations here. And I know you did that many times, that we just like I'm not saying anything new, right? Like in the review session, just like putting everything together in a collective way that you can think about the whole thing in an organized fashion. It's not new stuff. So this is the surface of the Earth. You exist somewhere here, and we define your location on the Earth using an angle we call lambda. So this lambda right here is your latitude. So you can exist on the northern hemisphere, or you can exist on the southern hemisphere, and that makes a difference. We'll talk about that. Hopefully we have some time. So what is the spherical coordinate system? This is the spherical coordinate system. Perpendicular to the surface of the Earth, that's r hat. So r hat comes like this, that's r hat. If you want to think about it like our flat Earth, of course, Earth is not flat, but this is like the ground that we see right here. This is a flat. If you zoom in on the surface of the Earth, you get a flat piece that we live on right now. So on this flat piece of the Earth, this is our perpendicular. So it's perpendicular to the Earth. That's Earth, that's our ground, that's our perpendicular to the whole. And then in the plane of the Earth that we live in right here, there is theta and phi. So like there's theta, hat, and phi hat. So theta hat and phi hat exist in our plane. Let me do it in a consistent way. This is phi hat. Maybe this. So just I want you to think about this. R hat is perpendicular to Earth. Theta hat and phi hat exist in our plane, such that the usual definition here for theta hat is going like this. In that sense, you should translate theta hat in your mind to be south. This is the south direction. Because if you exist in this latitude right here, and you move that way, with theta hat, you're going south. That's the south of the Earth. So the translation of r hat is perpendicular to the surface. The translation of theta hat is south. So theta hat is south, and negative theta hat is north. So theta hat covers north and south. Theta hat is south, negative theta hat is north. And then the final angle, like unit vector here is phi hat. Phi hat is like on the Earth, but the other way, east and west. So theta hat covers south and north, phi hat covers east and west. So phi hat in this picture usually goes into the picture. That's phi hat, and that's east. Because again, if you look at this picture right here, and if you go with phi hat, you're going east. That's east of the Earth. So the phi hat covers east and west. Phi hat itself is east, and negative phi hat is west. So this is a translation of the spherical coordinate system on the Earth. R hat perpendicular, theta hat south, opposite is north, phi hat is east, opposite is west. Any questions about the coordinate system here? And we're saying r hat cross theta hat is phi hat. Like the positive cross cycle starts with knowing that r cross theta is phi. Any question about the spherical coordinates here? Okay, so we have a little problem. Like we covered this in class, and like you've seen it many times. Again, it's not new, but just organizing your thing. We have a little problem in calculating Coriolis. What is the problem? Coriolis looks like that. The Coriolis force on Earth is minus 2m omega cross v prime. Okay? V prime is your own, the object that exists on Earth is moving on Earth. So V prime exists in the plane of the Earth. Like this V prime right here is in like either positive, negative theta hat or a positive, negative phi hat. You're moving north, you're moving south, you're moving east, you're moving south, east. You're moving in this plane of theta hat and phi hat. So V prime is gonna be given to you where like something is moving in this orientation. But it's gonna always be in theta hat or phi hat or negative. Yeah? So that's spherical coordinates. The little problem in calculating this Coriolis force here is the following. Omega as a vector does not exist completely as a spherical coordinate quantity. Omega is what? What's omega? The whole thing is spinning, so omega as a vector looks like this. This is omega, which is in k hat. Like if you want to like write it as a unit vector, this is k hat. K hat is not a spherical coordinate unit vector. It's a cylindrical coordinate. So you have this problem of this mismatch. The V prime vector is in spherical coordinates, because that's like what we live, the plane of the Earth is covered by theta and phi, the spherical coordinates. But omega of the spinning is in k hat. This k hat is not r, is not theta, is not phi, it's its own direction, because it's coming from cylindrical coordinates. That's like a separate kind of coordinate system. So we have these like clash between coordinate systems. So that's why we needed to take omega, which is from cylindrical. Why omega is cylindrical coordinates? Because omega is all about circular motion. This guy is going in a circle, perpendicular to circle, we call that k hat. Like we did circles with cylindrical coordinates. That's why omega comes from cylindrical coordinates, perpendicular to the circle. That's omega. But this is a sphere, has its own coordinate system. So this mismatch requires us to do the following, and you need to do this right here. You need to decompose omega into spherical coordinates. So now you can do the cross. So you want to decompose omega, which is in k hat, into spherical coordinates. Once you do that, once you write this omega in r hat, theta hat, phi hat, now you can perform the cross and you're done. That's a Coriolis problem. Okay. On Earth. So we want to decompose the omega vector and write it in terms of the spherical coordinate, just like V prime, so we can perform the cross completely in spherical coordinates. Any questions? Okay, so this vector decomposition of the vector omega into spherical coordinates matters which hemisphere you're in. If you're in the northern hemisphere, the decomposition takes a particular form. If you're in the southern hemisphere, it takes a different form, so be careful here. So let's look at the northern versus the southern hemisphere. Here is the northern hemisphere, so you exist as some lambda. This is r and theta. Phi hat is into the page, but omega doesn't have an r phi hat component. So let's do this. Let's try to do this decomposition. So the omega vector is pointing straight up. R hat and theta hat is like this. So the way that whenever I am about to decompose a vector, like a force of gravity or whatever, if I decompose a vector, the first thing I try to do is I'm gonna draw my axes, like the x and y, like the two axes that I want to decompose into, I'm gonna draw them completely, like do the full quadrants. I can see the full picture. I mean like this. I want to decompose into r hat and theta hat. So I'm gonna just like say, okay, this right here, these are my two axes. This is my x and y completely. So I can see like the four quadrants. So I'm trying to decompose into these axes. Right? So I draw them completely, like the x across. Okay. Why? Now I can see very clearly that the omega vector that I'm putting here exists in kind of the second quadrant of this coordinate system. In particular, if I want to take it and decompose it into r hat, it goes here. It has a positive r hat component. Because that's positive. But if I want to take it and decompose it into theta hat, it goes this is how it goes into theta hat, that's negative. That's against theta hat. So now I can see clearly that omega has a positive r hat component and has a negative theta hat component because it exists in the second quadrant of this coordinate system. Can you see that? Positive r hat, negative theta hat. And again, what we're doing, we are trying to decompose omega because it's in cylindrical. We cannot mix and match cylindrical and spherical. So we want to decompose omega into the spheres. So what I'm saying so far, this kind of picture showed me that omega is like positive something r hat, negative something theta hat. At least we know that. Let me expand this a little bit. It has a positive r hat, it has a negative theta hat component. Now, one of these components when you're decomposing is always one of them is sine the angle and one is cosine the angle. So let's see how do we determine? So first of all, I draw my axes completely. I can see now which is positive, which is negative. The second thing, I try to find an angle that this vector is making with one of the axes, one of the two axes. I try to find either of these two angles. If I know this or that, I can decompose. So let's figure out one of these two. Once you find it, you can find which is cosine, which is. So let's do a little like exercise here. If this angle is lambda, this also is lambda. Because lambda is between the horizontal and r hat. So this is lambda. Agreed? If this is lambda, then the one right next to it is 90 minus lambda. Because between horizontal and vertical. So this guy right here is 90 minus lambda. But then there is another 90 between this one and the next one. So the other one becomes lambda again. So what I'm saying is, at the end of the day, oops. Okay, this guy right here is lambda. That's from geometry, because this horizontal one is lambda, then 90 minus lambda, then goes back to lambda. So what am I doing? To decompose a vector, I need to know one angle it makes with either of the axes. Now that I know omega makes lambda with like theta hat, whenever like you decompose with the angle, that's cosine, because you're going to the adjacent of the angle. Like if you have a vector like this, and you know this angle right here is lambda or theta. If I look at this component right here, I'm going to the adjacent of the angle, because this angle is right here. That's the opposite. That's the adjacent. So if you take a vector and you decompose it with the angle that you know, that's cosine. You're going to adjacent. And the other one is sine. So what I'm saying here is, once I identify this to be my lambda, then with it is cosine, and against it is sine. So I'm saying basically the solution here is the theta hat is the cosine, and the other one is the sine. So it's omega sine lambda r hat and omega cosine lambda minus theta. Why cosine is in theta? Because I figured this to be theta. Going with theta, I'm decomposing into, that's like how I think about it quickly without drawing triangles. You can draw the, like many of you draw the triangle and try to figure it out. It could be a little bit confusing. But just like for me, once I identify an angle, decomposing with the angle is cosine. Always. Decomposing the other way from the angle is sine. So it's cosine, omega cosine minus theta hat, and omega sine plus r. So that's an exercise that you need to be very familiar with. How to write down the omega vector in spherical coordinates. Questions about it? Now, if you do it for the southern hemisphere, so be very careful which hemisphere you're doing. If you're doing for the southern hemisphere, this is how the picture looks like. So r hat is still outward from the sphere, theta hat is still south, omega is still up in k hat. So now, again, the first step I do is just I draw my axes completely so I can see what's going on. So this is my r hat, this is my theta hat. That's like, these are my two axes right here. So you can see now that omega exists in this quadrant right here. If you decompose it into into theta, you still get a negative theta component. It's against theta. If you decompose it to radial, now you get a negative radial. It's inwards. That's the difference. And you can follow, like, just to save time because I need to go soon, you can follow the same kind of geometry here and we'll find exactly the same result except for this minus. In the southern hemisphere, omega, the component of omega radially is inwards, is negative. But in the northern hemisphere, it was positive r hat. Southern, it will be negative r hat. So follow the same kind of idea and we'll find this negative omega sine lambda r hat, negative omega cosine lambda theta. So it's the same thing, except the r hat component changes sign. And this is very important because you're doing the cross between V and omega, so this minus sign will make a difference. That's why Coriolis acts one way in the northern hemisphere, acts the other way in the southern hemisphere. So this is a vector decomposition of omega into spherical coordinates. Questions about it? And we're not necessarily going to give you that, like you need to be able to decompose it yourself, like this. Any questions? All right, so now you're ready. Like once you decompose omega and you write it like that, you're ready because Now you can write down the force of Coriolis as minus 2m, this omega vector cross whatever v prime you're given. So v prime will be given to you in spherical coordinates. Your omega vector, depending on your hemisphere, will have a particular form. Now you can do the cross. That's like what the question will want. So let's look at this concept question here and do it, and then that's it. So in the exam, you're going to be given this definitely, but not necessarily this. Like, you need to know this. You need to know how to decompose omega, and you need to know that arc with theta is 5. Okay, so we are given that a particle is at a north latitude, so it's important, it's the northern hemisphere. And in the northern hemisphere, we just did the decomposition. It is positive omega sine lambda r hat minus omega cosine lambda theta. That's the northern. If it's so southern, then the r hat component is also negative. Okay, then you're traveling due north with v prime. You need to translate north. What is north? Well, theta hat is south. Look at theta hat, south, right? So when you say north, it is negative theta hat. So you should translate this into v prime is like some v prime negative theta hat. Because north is negative theta hat. So you need to be able to translate that. Again, I'm saying theta hat is south and phi hat is east. That's what you need to figure out. Then the other way is negative. North is negative theta hat, west is negative phi. So you're given v prime in negative theta hat, and now you have the expression for omega. All what is left is just to do the cross. That's like what we want you to do. So for example, here you say, okay, the Coriolis force is minus 2m. The expression for omega is omega sine lambda r hat minus omega cosine lambda theta hat cross minus v prime theta hat. That's this example here. Then you want to do the crosses. So you just follow the cross cycle r theta k, sorry, r theta phi. Right. If you write omega in cylindrical coordinates, it's omega k hat. But we don't want that. We want to convert it to spherical because we're crossing it with a spherical vector. V prime is a spherical coordinate vector, like it's a minus theta hat. That's spherical. So yes, we don't want the omega k hat form. We want to convert it into the spherical coordinates form. So for the question in the chat, well, if the question just wants direction, you can do that. But the question could also want the magnitude, like the actual force support. So you have to perform the full thing. Okay, so you need to be able to do the cross and like write down the full expression, because we could ask you for the full calculation. So let's do the full calculation here. So it looks like this. So we just need to like do the crosses. So we have an r hat cross theta hat, and we have a theta hat cross theta hat. Theta hat cross theta hat is 0. Like any two parallel vectors, there's no cross. So the second term we don't have to worry about. There's only the first term, so you get minus 2m omega sine lambda v minus v prime, then r cos theta, basically. And r cos theta just from our cycle is phi. That's positive. So you combine the negative here, cancel the negative there, and you get 2m omega sine lambda v prime phi hat. So that's the Coriolis force acting on you, which is east. So that's the kind of calculation we're interested in on the surface of the Earth. And it just happened here, by the way, that only one component survived because theta cross theta is 0. But if we started with v prime and like phi hat, for example, then you have two components, because r cross phi hat is not 0, and theta cross phi hat is not 0. So in general, you would have to like write down the two crosses and do both of them. And Luana in the chat was saying that we have found this kind of result, that in the northern hemisphere, we started north, we went east, like starting, if you write down the directions north, south, east, west, right? This is our compass, right? So in the northern hemisphere, this is the result of what we just found. In the northern hemisphere, this is what Coriolis does. If you move north, it pushes you east. Like this. And if you do, like, if you do the other combinations, if you start east, pushes you south, it goes like this. That's how Coriolis acts. That's Coriolis in terms of directions on the northern hemisphere. So if you want to like verify with that. And in the southern hemisphere, it goes the other way because of this extra minus sign in the r hat component, so it goes the other way. So that's what Coriolis does, northern or southern hemisphere. So like, let me just write here. But like, you should be able to do the full thing because we can ask you about the full calculation. So you should do the full thing, right? Omega in spherical coordinates, perform the cross with B prime that we give you. But Coriolis in the southern hemisphere goes the other way. If you start north, it pushes you west. If you start west, it pushes you south, etc. So that's it. That's like, I think the important part about Coriolis is figuring out this vector decomposition of omega, which is like right here, northern or southern, and then doing the cross with whatever V prime will give you. That's how you get the Coriolis force. I think that's like the most important application for Coriolis. So, any questions? All right, that's it from my side. Yeah, thank you so much. The structure of the test, like I cannot say definitely, but it's kind of similar to the midterms, except it's longer. So it's like maybe 1 time like and a half like of a regular test, but same. Thank you so much, everyone. So yeah, it's the same kind of analytical problems, short problems, concept questions, but like longer, like 1.5 times longer. All right, thank you so much, everybody, for a great semester. I really enjoyed like working with you all. I cannot say how many problems, like I cannot share that. There was another question, little more. Yeah, the final is on this, okay? Like this set of topics and this set of practice problems. Okay? Thank you so much. All right, my friends, it was a pleasure. I will be teaching 822, so I will see you in 822 next semester, and I will run review sessions for 822. So I will see you around again, and I really enjoyed all of your questions and all of your interactions. And if you have any questions over the weekend, let me know, like, come around. All right. Thank you so much.